Hello there, and welcome to Science for Sleep. Where curiosity settles in, the universe feels a little closer, and complicated ideas take their time, moving gently enough to let your thoughts slow down along the way. Tonight, we're setting out on a journey farther than any human being has ever travelled. Past the planets, beyond the familiar glow of the sun, and into a region so distant and quiet that even sunlight becomes faint and thin. Our story begins with two small spacecraft, each no larger than a modest car, drifting steadily through the darkness for decades. They were launched in the 1970s, long before smartphones, long before the internet connected the world, long before many of us listening now were even born. And yet, even today, they continue to send messages back to Earth, whispering across unimaginable distances about a place no one had ever seen before. What they found out there surprised scientists in ways that few missions ever have. Not because the edge of the solar system was completely unknown, but because reality turned out to be stranger, more complex, and in some ways more beautiful than anyone expected. Before we drift any farther into that story, I'd like to ask you something gentle and simple. Where are you listening from tonight? Are you in a quiet room with the lights low, or perhaps under a blanket, or maybe sitting by a window where the night sky is visible? And what time is it where you are right now? It feels fitting somehow to think about time while we talk about spacecraft that have been travelling longer than many people have been alive, carrying pieces of our world into the deep dark between the stars. If you find this journey soothing or interesting, or simply a pleasant way to unwind after a long day, I'd be grateful if you considered liking the video or subscribing. It helps this small, quiet corner of science reach others who might need a calm place to rest their thoughts for a while. Now, let's settle in and begin, slowly, without rushing, because this is not a short trip. It's a journey measured in billions of kilometres, in decades of silent travel, in signals that take nearly a full day just to reach us. Imagine for a moment standing on a shoreline at night. The water stretches out into darkness, and you can't see where it ends. You know the shore is behind you, solid and familiar, but ahead there is only distance. The solar system, in a way, has a shoreline too. Not a sharp boundary, not a wall, but a vast region where the influence of our sun begins to fade and something else begins to take over. For most of human history, we didn't even know such a boundary existed. The planets were the main landmarks of the solar system: Mercury, Venus, Earth, Mars, the gas giants beyond. Later, we discovered asteroids, comets, and distant icy worlds, but the idea that the sun itself creates a kind of bubble in space, a protective cocoon blown outward by its own energy, came much later. And even after scientists understood that this bubble existed, no one knew exactly where it ended, or what waited beyond it. That's where Voyager comes in. The Voyager spacecraft were never originally designed to leave the solar system entirely. Their primary mission was to visit the giant planets, Jupiter and Saturn, and in the case of Voyager 2, Uranus and Neptune as well. These flybys alone were historic, revealing volcanoes erupting on distant moons, storms larger than Earth itself, and rings and magnetic fields more complex than anyone had imagined. But once those encounters were complete, the spacecraft kept going. There was no reason to stop them. They still had power, their instruments still worked, and the silence ahead of them was filled with questions. So they continued year after year, moving farther from the sun, slipping past the orbit of Pluto, heading toward a region that had never been explored. At first, the changes were subtle. Sunlight grew weaker, though still bright enough to power instruments and cameras. The density of particles streaming outward from the sun, known as the solar wind, began to decrease. The environment around the spacecraft grew quieter, emptier, calmer in some ways, but also more mysterious. Scientists on Earth watched the data closely, waiting for signs that Voyager was approaching the boundary of the sun's influence. But what they found was not a simple crossing, not a clear line marking the end of one region and the beginning of another. Instead, it was gradual, complex, and filled with surprises. One of the first hints came from the behaviour of charged particles. The solar wind, which flows outward from the sun in all directions, slows down as it pushes against the thin gas and magnetic fields of interstellar space. Somewhere far beyond Pluto, this wind begins to pile up, forming a turbulent region where particles swirl and collide in unpredictable ways. Voyager entered this region decades after launch, and the instruments began to detect changes that scientists had only predicted in theory. The speed of the solar wind dropped, the density of certain particles increased, magnetic fields shifted in subtle but measurable ways. It was like approaching a distant coastline in fog. You can't see the shore yet, but the waves begin to change, the air smells different, and you sense that something ahead is altering the environment around you. At this point in the journey, the spacecraft was so far away that even radio signals took more than 15 hours to travel one way. Commands sent from Earth had to be carefully planned, because any mistake would take nearly a full day to correct. And yet, despite this enormous distance, Voyager continued to function, its instruments patiently recording the conditions of a region no human-made object had ever explored. What makes this story especially remarkable is the timescale involved. The engineers who built Voyager in the early 1970s could not possibly have known that their spacecraft would still be operating half a century later. Many of them have long since retired, and some are no longer alive, yet the machines they designed continue to send back data, like messages in bottles drifting across a cosmic ocean. There is something quietly moving about that thought. A group of people, decades ago, working carefully, tightening bolts, soldering circuits, testing instruments, knowing that their work might outlast them, might travel farther than any human being could ever go. And now, those spacecraft are farther from Earth than any other objects we've ever created. As Voyager moved outward, scientists began to notice something unexpected about the boundary region itself. They had imagined it might be smooth, like the surface of a balloon, with a relatively clear transition from the solar wind to interstellar space. Instead, the data suggested a much more complicated structure, with waves, ripples, and regions of turbulence that behaved in ways no one had fully predicted. It turned out that the edge of the solar system was not a quiet frontier at all. It was active, dynamic, and in some ways surprisingly noisy, filled with interactions between particles and magnetic fields that produced faint signals detectable even across billions of kilometers. One of the most striking discoveries came when Voyager's instruments detected oscillations in the plasma around the spacecraft, vibrations that scientists converted into sound. The result was an eerie, rising tone, a kind of cosmic hum that revealed the density of interstellar gas. Hearing that sound for the first time was a powerful moment for many researchers. It was, in a sense, the first time humanity had heard the space between the stars, not as silence, but as something with structure, with texture, with subtle variations that told a story about the environment beyond our solar system. And yet, even as these discoveries unfolded, Voyager continued drifting outward, farther into a region where the sun is no longer the dominant influence. The particles streaming from distant stars, the faint magnetic fields threading through the galaxy, the remnants of ancient supernova explosions, all of these begin to shape the environment in ways very different from the space close to home. It's easy to think of space as empty, but it's never truly empty. Even in the vast distances between stars, there are atoms, fields, and waves of energy moving slowly through the darkness. Voyager is now travelling through this interstellar medium, sampling it, measuring it, sending back tiny fragments of information that help us understand the galaxy we live in. And perhaps the most surprising part of all is that this journey is still ongoing. Even now, as you listen to this, Voyager is still out there, moving steadily, slowly, carrying with it a golden record engraved with sounds and images from Earth, a kind of time capsule meant for anyone or anything that might one day find it. The chances of that record ever being discovered are extremely small, of course. Space is vast beyond comprehension, and the distances between stars are measured in trillions of kilometres. But the act of sending that message, of placing a small piece of our world on a spacecraft bound for the stars, says something about us as a species. It says that we are curious, that we are hopeful, that we are willing to reach outward even when the distances are almost unimaginable. In the quiet darkness far beyond the planets, Voyager continues its slow passage, and the data it sends back continues to reshape our understanding of where the solar system ends and where the rest of the galaxy begins. And to truly appreciate what Voyager found, it helps to step back for a moment and consider something fundamental, something easy to overlook. What exactly is the solar system, and where does it really end? Not long before Voyager ever reached the deep, quiet outskirts of the solar system, its story began in a time when space exploration still felt new, daring, and uncertain. The early 1970s were an era when computers filled rooms, when spacecraft were guided by calculations written by hand and checked again and again, and when sending a machine beyond the planets required both careful planning and a fair amount of courage. By then, humanity had already walked on the moon. Probes had visited Mars and Venus. A few spacecraft had even flown past Jupiter and Saturn, offering brief glimpses of their swirling clouds and mysterious moons. But no mission had ever attempted what Voyager was about to do, a journey that would not only visit the giant planets, but continue onward, farther than any spacecraft had ever travelled. The idea began with something simple, almost accidental, a rare alignment of the outer planets. Roughly every 175 years, Jupiter, Saturn, Uranus, and Neptune line up in such a way that a spacecraft can visit them one after another, using each planet's gravity to slingshot itself onward. This technique, called a gravity assist, allows a spacecraft to gain speed without carrying enormous amounts of fuel. It is, in a sense, a way of borrowing momentum from a planet as it moves around the Sun. Scientists realized that such an alignment would occur in the late 1970s. If a spacecraft were launched at just the right time, it could visit multiple planets in a single mission, something that had never been done before. The opportunity was too good to miss, but it also came with challenges. The spacecraft would need to survive for many years, operate far from the Sun where sunlight is weak, and carry instruments capable of studying worlds that no one had ever seen up close. Engineers and scientists began designing what would eventually become the Voyager probes. They needed to be robust, reliable, and capable of functioning in extreme cold and radiation. Every component had to be carefully chosen, tested, and tested again. Repairs would be impossible once the spacecraft left Earth. Whatever was launched would have to keep working year after year, alone in the silence of space. At the Jet Propulsion Laboratory in California, teams worked long hours assembling the spacecraft, wiring instruments, and writing the software that would guide them across billions of kilometers. There was a quiet understanding among them that this mission was different. It wasn't just about visiting a planet and returning data. It was about sending something into the unknown, into regions no one had ever explored. The spacecraft themselves were marvels of engineering for their time. Each carried cameras, spectrometers, magnetometers, and detectors designed to measure charged particles and cosmic rays. They were powered not by solar panels, which would have been useless so far from the Sun, but by radioisotope thermoelectric generators, devices that convert heat from decaying plutonium into electricity. These generators could provide power for decades, slowly fading but never stopping abruptly. One of the most unusual features of the spacecraft was something that had nothing to do with science at all, at least not in the usual sense. Bolted to the side of each Voyager was a golden record, a phonograph record made of gold-plated copper, containing sounds and images from Earth. There were greetings in dozens of languages, music from different cultures, the sound of waves on a shore, the laughter of a child. The record was not meant to be practical. The chances of it ever being found were, and still are, extraordinarily small. But it was included as a kind of gesture, a message in a bottle cast into the cosmic ocean, a way of saying, this is who we are. As the launch dates approached, the tension grew. Launching a spacecraft is always risky. Rockets are powerful but unforgiving machines, and a single malfunction can end a mission before it even begins. Engineers checked and rechecked every system. Simulations were run, trajectories calculated, backup plans prepared. Then, in August of 1977, Voyager 2 lifted off from Cape Canaveral, riding a column of flame into the sky. A few weeks later, in September, Voyager 1 followed. The numbering may seem backward, but Voyager 1 was placed on a faster trajectory that would reach Jupiter and Saturn sooner. For the teams who had worked on the mission, those launches were both exhilarating and bittersweet. Years of preparation had led to this moment, and now the spacecraft were on their own, leaving Earth behind, heading toward destinations that existed only as tiny points of light in telescopes. The early months of the journey were filled with careful monitoring. Engineers tracked the spacecraft's health, adjusted their trajectories, and ensured that every instrument was functioning properly. Signals from Voyager travelled at the speed of light, but even so, the distances were already enormous. It took minutes for commands to reach the spacecraft and minutes more for confirmations to return. Gradually, the probes moved farther from Earth, and the sun began to shrink into a smaller, brighter star behind them. The inner planets fell away one by one, and the cold, dark region of the outer solar system stretched ahead. Years passed before Voyager reached its first major destination, Jupiter. When it did, the images it sent back were unlike anything anyone had seen before. Storms larger than Earth churned in the planet's atmosphere. Lightning flashed in towering clouds. And on the small moon, Io, volcanoes erupted. The first active volcanoes ever observed beyond Earth. These discoveries alone would have made the mission historic, but Voyager was only beginning. After Jupiter came Saturn, with its intricate rings and dozens of moons. Voyager 2 would go on to visit Uranus and Neptune as well, revealing pale blue worlds, dark storms, and winds faster than any on Earth. With each encounter, the spacecraft used the gravity of the planets to change course and gain speed, slinging outward, faster and farther than any probe before them. By the time the planetary tour was complete, Voyager had achieved something extraordinary. It had explored the giant planets and was now heading toward a region that no spacecraft had ever entered, the vast expanse beyond the known frontier of the solar system. At that point, a decision had to be made. The primary mission was over. The spacecraft had already exceeded expectations. Some might have considered the job finished. But the instruments were still working, the power supplies were still generating electricity, and ahead lay a destination that had never been reached. The distant boundary where the influence of the sun begins to fade and interstellar space begins. So the mission was extended. Voyager would keep going year after year, drifting outward, sending back data about the environment of the outer solar system, measuring particles, magnetic fields, and radiation. There was no guarantee of what it would find. Scientists had theories about the heliosphere, the vast bubble carved by the solar wind, but no one knew exactly where its boundary lay or what conditions would be like there. It was a region defined more by models and equations than by direct observation. As the spacecraft travelled farther, the sun grew dimmer, and the temperature of the surrounding space dropped to levels difficult to imagine. The signals returning to Earth became weaker, requiring massive radio antennas to detect them, dishes tens of meters across, listening carefully for faint whispers from billions of kilometers away. Despite the distance, communication continued. Commands were sent, instruments calibrated, data recorded and analysed. The spacecraft moved steadily onward, covering millions of kilometers each day, yet the scale of the solar system was so vast that progress still felt slow, almost patient. as if the journey itself required a kind of quiet persistence. For the scientists and engineers who followed the mission, Voyager became something more than a spacecraft. It was a companion, a tiny emissary moving through a region no one had ever seen, reporting back in the language of numbers and signals. And as the years turned into decades, something remarkable happened. Voyager did not fail. Its systems aged, its power slowly declined, but it kept working, kept sending data, kept moving outward. There is something humbling about that persistence. A machine built by human hands, launched in an era of typewriters and slide rules, still travelling, still exploring, still expanding our understanding of the universe. Eventually, as Voyager continued its journey, the environment around it began to change in subtle ways. The solar wind weakened, the density of certain particles increased, magnetic fields behaved differently. These were the first signs that the spacecraft was approaching a boundary, a region where the sun's influence was giving way to something larger, something that extended across the galaxy itself. It's easy to picture the solar system as something tidy and compact. In most diagrams, the sun sits at the centre, the planets are arranged in neat orbits, and beyond Neptune there's often just empty space fading into black. That picture is useful for teaching, but it leaves out something important. The solar system is not just the region where the planets orbit. It extends far beyond them, reaching into distances so vast that even light takes many hours to cross them. To understand why this is true, it helps to start with a simple question. Where does the solar system actually end? Is it the orbit of the last planet, the outer edge of the Kuiper belt, the distant Oort cloud, or is it something less visible, something defined not by objects but by influence? For a long time, astronomers thought of the solar system mainly in terms of the planets. The farthest known planet was Neptune, orbiting about 4.5 billion kilometers from the Sun. That already seemed unimaginably distant. Light from the Sun takes more than 4 hours to reach Neptune, and a spacecraft travelling at tens of thousands of kilometers per hour still needs more than a decade to get there. Then, in the early 20th century, astronomers began discovering icy objects beyond Neptune, a vast population of small worlds now known as the Kuiper belt. Pluto turned out to be just one of many. Some of these objects follow elongated orbits, swinging far out into space before returning closer to the Sun. That discovery stretched the boundaries of the solar system in people's minds, but it was only the beginning. Far beyond the Kuiper belt lies the Oort cloud, a spherical halo of icy bodies that may extend tens of thousands of astronomical units from the Sun. An astronomical unit, or AU, is the average distance between Earth and the Sun, about 150 million kilometers. So when we talk about tens of thousands of AU, we're speaking of distances so large that they become difficult to visualize. If Earth were 1 meter from the Sun in a scale model, Neptune would be about 30 meters away, roughly the length of a large swimming pool. But the inner edge of the Oort cloud would be several kilometers away, and its outer boundary could extend halfway to the nearest star. And yet, even that enormous cloud of distant comets is not the full story. Because the solar system is not defined only by objects bound in orbit around the Sun. It is also defined by the region where the Sun's influence dominates over the rest of the galaxy. The Sun is not just a source of light and heat, it is also a source of charged particles, a constant stream flowing outward in all directions. This stream is called the solar wind, and it carries with it the Sun's magnetic field, pushing against the thin gas and magnetic fields that fill interstellar space. As the solar wind expands outward, it creates a vast bubble known as the heliosphere. Inside this bubble, the environment is shaped primarily by the Sun. Outside it, the conditions are dominated by the galaxy itself. For decades, scientists could only estimate the size of the heliosphere. They knew it had to exist, but its exact shape and extent were uncertain. Models suggested it might extend 100 astronomical units or more from the Sun, but there was no direct measurement, no spacecraft that had travelled far enough to confirm it. This is where Voyager's journey became so important. By the time it passed the orbit of Pluto, Voyager was already farther from the Sun than any spacecraft before it. But even at that distance, it was still well inside the heliosphere, still within the protective bubble of the solar wind. That realization surprised many people. Pluto feels remote, cold, and distant, yet it lies far from the true boundary of the Sun's influence. The solar system, in terms of its environment, stretches much farther than the outermost planet. One way to think about it is to imagine a campfire on a dark night. Close to the fire, the warmth is strong and the light is bright. Step back a few meters, and you can still feel the heat, though less intensely. Walk farther, and the warmth fades, but you can still see the glow. Eventually, at some distance, the fire no longer warms you at all, and its light becomes just another faint point in the darkness. The Sun works in a similar way, though on a vastly larger scale. Its light travels outward indefinitely, but its particles and magnetic fields have a more limited reach. The heliosphere marks the region where those particles and fields dominate, where the Sun's presence is still the main factor shaping the space around it. As Voyager travelled outward, its instruments began to detect changes in that environment. The density of solar wind particles decreased. The magnetic field became more variable. Cosmic rays, high-energy particles originating from distant supernova explosions and other energetic events in the galaxy, began to increase in number. These changes were subtle at first, but they grew more pronounced as the spacecraft moved farther from the Sun. It was like walking away from a city at night. At first, the noise fades slowly. The glow of lights dims gradually, and only after some distance do you realize how quiet and dark the surroundings have become. Another surprise was the structure of the heliosphere itself. Early models often depicted it as a smooth, comet-shaped bubble, with a rounded front facing the direction of the Sun's motion through the galaxy, and a long tail stretching behind. But the data from Voyager suggested that the boundary regions were more complex, with turbulence, waves, and regions of compressed plasma that behaved in ways not fully predicted. Scientists began to realize that the solar system was not just larger than they had imagined, but also more dynamic, more interactive with the surrounding galaxy. The boundary between solar and interstellar space was not a clean dividing line. It was a region of interaction, where particles and magnetic fields from two different environments met and influenced each other. To grasp the scale of this boundary, consider the distances involved. Voyager 1 crossed the heliopause, the outer boundary of the heliosphere, at about 121 astronomical units from the Sun. That is more than 3 times the distance to Pluto, and even that crossing did not mean the spacecraft had left the solar system entirely in every sense, since the gravitational influence of the Sun extends much farther, reaching into the distant Oort cloud. So the solar system has multiple boundaries, depending on how you define it. There is the region of the planets, the realm of the Kuiper belt, the distant sphere of the Oort cloud, and the vast bubble of the heliosphere. Each of these layers adds another dimension to our understanding of how large our cosmic neighbourhood really is. For people in earlier centuries, the solar system was thought to end at Saturn. Later, Uranus and Neptune extended its known limits. The discovery of Pluto and the Kuiper belt pushed it farther still. And now, thanks to Voyager, we know that the Sun's influence reaches far beyond anything that can be seen with a telescope alone. There is something quietly astonishing about that realization. Our star, one among hundreds of billions in the Milky Way, carves out a region of space that stretches billions upon billions of kilometers in every direction, and within that region, tiny worlds like Earth orbit, carrying oceans, clouds, and living creatures who are only now beginning to understand the scale of the environment around them. As Voyager continued its outward journey, the spacecraft moved deeper into regions where the solar wind slowed and began to pile up, forming a kind of boundary layer. Scientists called this region the heliosheath, a turbulent zone where particles from the Sun interact with particles from interstellar space. The heliosheath turned out to be far more complex than anyone had expected. Instead of a simple transition, it was filled with fluctuations, shocks, and waves of charged particles. Voyager detected sudden changes in particle density and magnetic fields, signs that the spacecraft was moving through a region shaped by powerful but invisible forces. One of the most intriguing discoveries was the gradual increase in cosmic rays as Voyager approached the heliopause. Inside the heliosphere, the solar wind and magnetic field help shield the inner solar system from many high-energy particles. But near the boundary, that shielding weakens, and the intensity of cosmic rays rises. This was one of the clearest signs that Voyager was nearing interstellar space. It was like approaching the edge of a forest and noticing that the wind grows stronger and the sounds change. Subtle clues that the environment is shifting. Even now, the scale of the solar system remains difficult to grasp. The distances are so vast that ordinary comparisons often fall short. Yet Voyager's journey provides a kind of map, a path traced slowly outward, showing that the region shaped by our Sun extends far beyond the familiar orbits of the planets. And as scientists studied the data, they began to ask new questions. If the heliosphere is shaped by the interaction between the solar wind and the interstellar medium, what determines its exact size and shape? How does it change over time as the Sun moves through different regions of the galaxy? And what does the environment beyond it really look like? Long before Voyager ever approached the boundary of interstellar space, it spent years travelling through something that cannot be seen, cannot be felt, and yet fills the entire solar system. This vast, invisible flow is called the solar wind, and although the name suggests a gentle breeze, it is in reality a continuous stream of charged particles racing outward from the Sun at speeds of hundreds of kilometers per second. To picture it, it helps to set aside the common image of space as completely empty. Space is extraordinarily thin compared to the air we breathe, but it is not a perfect vacuum. The Sun constantly releases particles, mostly electrons and protons, from its outer atmosphere, the corona. These particles escape the Sun's gravity and spread outward in all directions, carrying with them the Sun's magnetic field. If you could somehow see this process, the Sun would not look like a quiet, glowing sphere hanging in darkness. It would appear more like a source at the centre of a vast, expanding current, an ocean of energy and particles flowing outward in every direction, passing the planets, sweeping beyond Pluto, and continuing for billions of kilometers before gradually slowing and merging with the environment between the stars. This flow never stops. Every second, the Sun sheds millions of tons of material into space. That may sound enormous, but the Sun is so massive that even over billions of years, it loses only a tiny fraction of its total mass. For the solar system, however, this steady outpouring shapes nearly everything about the environment between the planets. Earth itself exists within this stream. The solar wind passes our planet constantly, but we rarely notice it because Earth has a magnetic field that deflects most of these charged particles. When especially strong bursts of solar wind arrive, they can interact with our atmosphere and produce auroras, the shimmering curtains of light seen near the polar regions. Those quiet, glowing colours in the night sky are visible reminders that our planet is immersed in this invisible ocean. Farther from the Sun, the solar wind continues to expand, spreading thinner and thinner as it travels. Near Earth, the particles are relatively dense and energetic. By the time they reach the outer planets, they are more diffuse, though still moving rapidly. And beyond those distant worlds, the solar wind becomes increasingly faint, yet it does not simply vanish. It keeps going, pushing outward against the faint gas and magnetic fields of interstellar space. For scientists, understanding the solar wind has always been essential to understanding the size and structure of the solar system. The heliosphere, the enormous bubble created by this outward flow, exists because of the solar wind. Without it, the Sun would still shine, but its influence would not extend nearly as far. When Voyager began its journey beyond the outer planets, it entered a region where the solar wind had never been directly measured. Instruments aboard the spacecraft were designed to detect charged particles, magnetic fields, and plasma waves, allowing scientists to study this distant environment for the first time. At first, the solar wind behaved largely as expected. The particle density decreased with distance from the Sun, and the magnetic field grew weaker. But as Voyager travelled farther, something interesting began to happen. The speed of the solar wind started to change. The reason lies in what happens when an outward-moving flow meets resistance. Even though interstellar space is incredibly thin, it is not completely empty. It contains atoms, ions, and magnetic fields drifting slowly through the galaxy. As the solar wind expands outward, it eventually encounters this interstellar medium, and the two begin to interact. Imagine a river flowing steadily until it reaches the ocean. Near the mouth, the current becomes more complex. Waves form, currents collide, and the motion of the water becomes less predictable. In a similar way, the solar wind does not simply stop at a sharp boundary. Instead, it slows, compresses, and becomes turbulent as it approaches the outer limits of the heliosphere. Voyager detected the first signs of this slowdown years before reaching the actual boundary. The instruments recorded changes in the speed and temperature of the solar wind, along with fluctuations in the magnetic field. These changes indicated that the spacecraft was entering a region where the outward pressure of the solar wind was being balanced by the pressure of the interstellar medium pressing inward. Scientists call the point where the solar wind slows from supersonic to subsonic speeds the termination shock. This name might sound dramatic, but the phenomenon is somewhat similar to what happens when a jet aircraft slows below the speed of sound, except on a scale measured in billions of kilometers. Voyager 1 crossed the termination shock in 2004, at a distance of about 94 astronomical units from the Sun. Voyager 2 crossed it a few years later, at a slightly different distance, revealing that the boundary was not perfectly spherical. The heliosphere, it turned out, was shaped by forces both inside and outside, including the Sun's activity and the pressure of interstellar space. Beyond the termination shock lies the heliosheath, a vast region where the solar wind continues to flow outward, but at slower speeds, becoming hotter and more turbulent. This region is difficult to imagine because it is unlike anything in everyday experience. It is not a solid surface or a visible cloud. It is a region defined by changes in the motion and energy of particles, by subtle shifts in magnetic fields, and by waves moving through plasma so thin that even the best vacuums on Earth would seem dense by comparison. As Voyager moved through the heliosheath, the environment around it became increasingly complex. Particle detectors recorded sudden increases and decreases in intensity, suggesting that the region was filled with structures and boundaries of its own. Magnetic field measurements revealed unexpected orientations, hinting that the interaction between the solar wind and interstellar space was far more intricate than simple models had predicted. One of the most intriguing aspects of the solar wind is that it carries the Sun's magnetic field with it, stretching it outward into a spiral pattern as the Sun rotates. This structure, known as the Parker spiral, creates a vast magnetic architecture throughout the heliosphere. Charged particles move along these magnetic field lines, and their behavior can be influenced by even small changes in the field's strength or direction. For Voyager, travelling through this environment was like drifting through a shifting, invisible landscape. There were no landmarks, no visible features, only the data transmitted back to Earth, numbers and graphs that scientists studied carefully, searching for patterns that might reveal the structure of this distant region. Communication with the spacecraft required patience. By this stage of the journey, radio signals took more than 16 hours to travel one way. Engineers and scientists had to plan their commands carefully, knowing that any response would not be received until the following day. It was a kind of conversation conducted across nearly a full day of silence, each exchange separated by vast distances and long waits. Meanwhile, the spacecraft itself continued steadily outward, powered by the slow decay of plutonium in its radioisotope generators. The available power decreased year by year, forcing mission controllers to turn off some instruments to conserve energy for the most critical measurements. Every watt became precious, every decision carefully considered, because the data Voyager was sending back could not be obtained in any other way. As the solar wind weakened farther from the Sun, another population of particles began to play a more prominent role. These were cosmic rays, high-energy particles originating from outside the solar system, accelerated by events such as supernova explosions. Inside the heliosphere, the solar wind helps shield the inner planets from many of these particles. But near the outer boundary, that shielding becomes less effective and the intensity of cosmic rays increases. Voyager's instruments recorded this gradual rise, providing another clue that the spacecraft was approaching the edge of the Sun's influence. It was like noticing a change in the background noise of a room, subtle at first, then unmistakable. The temperature of the plasma in the heliosheath also surprised scientists. Models had predicted certain values, but the measurements revealed conditions that were different in important ways, suggesting that energy was being distributed through the region differently than expected. The interactions between particles, magnetic fields, and waves were more complex than the simplified theories had assumed. All of this reinforced an important realization. The solar wind does not simply carve out a static bubble in space. The heliosphere is dynamic, changing over time as the Sun's activity rises and falls in its approximately 11-year cycle. Periods of intense solar activity send stronger bursts of particles outward, while quieter periods produce weaker flows. These variations propagate outward through the heliosphere, altering its structure over years and decades. Voyager, moving steadily outward, effectively travelled through a changing environment, one shaped not only by distance but also by time. The conditions at a given location depended on what the Sun had been doing years earlier, because it takes time for the solar wind to travel such immense distances. This introduces a curious way of thinking about the outer solar system. In some sense, Voyager was moving through layers of history, encountering regions of space influenced by solar activity that had occurred long before. The particles and magnetic fields surrounding the spacecraft carried information about the Sun's past, preserved in the structure of the solar wind as it expanded outward. Gradually, as the spacecraft continued its journey, the changes became more pronounced. The solar wind slowed further. The density of interstellar particles increased. Magnetic field measurements suggested that the influence of the galaxy was beginning to rival that of the Sun. Scientists began to realize that Voyager was approaching the outer boundary of the heliosphere, the heliopause, where the outward pressure of the solar wind is balanced by the pressure of interstellar space. This boundary is not a wall or a sharp edge, but a transition region, shaped by complex interactions that were only now being observed directly for the first time. Reaching that boundary would mark a historic milestone, the first time a human-made object entered interstellar space. But even before the crossing itself, the journey through the solar wind had already transformed our understanding of the solar system. It revealed that the space between the planets is not empty, that the Sun's influence extends far beyond what we can see, and that the boundary between our cosmic neighbourhood and the rest of the galaxy is a place of subtle and fascinating interactions. By the time Voyager was moving through the outer reaches of the solar wind, scientists had already spent decades trying to understand a boundary that no telescope could see, and no human could visit directly. This boundary had a name, the heliosphere, but for a long time it existed mostly in equations, diagrams, and educated guesses. It was something inferred rather than observed, a structure predicted by theory but still waiting to be explored in reality. To understand what the heliosphere is, it helps to think again about the solar wind, that steady outward flow of charged particles leaving the Sun in every direction. The Sun is constantly releasing this material, and because the particles are electrically charged, they carry the Sun's magnetic field with them, As this flow expands outward, it fills a vast region of space, pushing against the thin gas and magnetic fields that drift between the stars. The heliosphere is the region where the solar wind dominates, where the environment is shaped primarily by the sun rather than by the galaxy. Inside this bubble, the particles, fields, and radiation we encounter are mostly products of our own star. Outside it, the influence of other stars, ancient supernovae, and the interstellar medium becomes stronger. What makes the heliosphere difficult to imagine is that it has no visible surface. There is no glowing edge, no sharp line, no boundary you could point to in the sky. It is defined by changes in pressure, particle density, and magnetic fields, subtle transitions rather than dramatic ones. For many years, scientists could only estimate its size. They knew the solar wind must eventually slow down and merge with the interstellar medium, but where exactly that happened was uncertain. Some models suggested the boundary might lie about 50 astronomical units from the Sun, others placed it much farther out. Without direct measurements, there was no way to know for sure. One way to picture the heliosphere is to imagine a campfire burning on a still night. The heat and smoke rise and spread outward, forming a region where the air is warmer and more turbulent than the surrounding darkness. Step far enough away and the warmth fades, replaced by the cooler air of the night. The transition is gradual. There is no line on the ground marking where the warmth ends and the cold begins, yet the difference is real. The heliosphere works in a similar way, though instead of warm air it consists of plasma, a mixture of charged particles and magnetic fields, expanding outward from the sun. And instead of meeting cool night air, it encounters the interstellar medium, a sparse but persistent mixture of atoms, ions, and cosmic rays drifting through the galaxy. The boundary between these two regions is shaped by a balance of pressures. The solar wind pushes outward, while the interstellar medium presses inward. Where these forces meet, the solar wind slows, compresses, and eventually gives way to the conditions of interstellar space. Scientists divide this outer region into several layers. First comes the termination shock, where the solar wind slows abruptly from supersonic to subsonic speeds. Beyond that lies the heliosheath, a turbulent zone where the slowed solar wind continues outward, heated and compressed. And finally there is the heliopause, the outer boundary where the pressure of the solar wind is balanced by the pressure of interstellar space. Before Voyager, all of this was theoretical. Researchers had models and simulations, but no direct observations. It was like trying to understand the structure of an ocean by watching waves from the shore, knowing there must be currents and depths and distant horizons, but having no ship to explore them. As Voyager travelled outward, it became that ship. Its instruments began measuring changes in particle speeds, densities, and magnetic fields, providing the first real evidence of the heliosphere's structure. One of the surprising discoveries was that the heliosphere is not perfectly round. The Sun is moving through the galaxy, orbiting the centre of the Milky Way at hundreds of kilometres per second. As it moves, the interstellar medium flows past it, shaping the heliosphere much like wind shapes the smoke from a chimney. The bubble is compressed on the side facing the Sun's direction of motion, and stretched out behind, forming something like a long trailing tail. Even this description, however, turned out to be an oversimplification. Data from Voyager and other missions suggested that the heliosphere's shape is influenced not only by the solar wind and interstellar gas, but also by magnetic fields threading through the galaxy. These fields can twist and distort the boundary, creating structures that are far more complex than a simple comet-like shape. Another surprise was the level of turbulence near the boundary. Scientists had expected a relatively smooth transition, but Voyager detected fluctuations and irregularities, regions where particle densities changed suddenly, or magnetic fields shifted direction. It was more like the choppy waters near a shoreline than the calm surface of a pond. There is also something quietly remarkable about the scale of the heliosphere. The distance from the Sun to the heliopause is more than 100 times the distance from Earth to the Sun. Light takes many hours to travel that far. A spacecraft moving faster than any airplane ever built still needs decades to reach it. And yet, in galactic terms, the heliosphere is small. The nearest star is more than 4 light-years away, tens of thousands of times farther than the heliopause. Our Sun's protective bubble is just a tiny pocket in an enormous galaxy, a local clearing in a vast cosmic forest. Inside this bubble, the solar wind plays an important role in shielding the inner solar system from many high-energy cosmic rays. These particles, accelerated by supernova explosions and other energetic events, can damage electronics and living tissue. The heliosphere acts as a kind of filter, reducing the intensity of this radiation before it reaches the planets. This shielding effect means that the heliosphere is not just an abstract scientific concept. It has real consequences for life on Earth and for any spacecraft travelling beyond the planets. As Voyager approached the heliopause, its instruments recorded a steady increase in cosmic ray intensity, a clear sign that the spacecraft was moving into a region where the Sun's protective influence was weakening. Another fascinating aspect of the heliosphere is that it is not static. The solar wind varies with the Sun's activity, which follows an approximately 11-year cycle. During periods of high activity, the solar wind is stronger, and the heliosphere can expand slightly. During quieter periods, it may contract. These changes propagate outward over years, meaning that the outer boundary is constantly shifting, breathing in and out on timescales far longer than a human lifetime. This dynamic nature makes the heliosphere difficult to define precisely. It is not a rigid shell, but a living structure, shaped by flows of particles and fields changing slowly but continuously. Voyager, travelling outward at a steady pace, encountered conditions influenced by solar activity that had occurred years earlier, carried outward by the solar wind like ripples spreading across a pond. There is also the question of how the heliosphere interacts with the local interstellar medium. The region of space through which our Sun is currently moving is known as the local interstellar cloud, a relatively warm and diffuse cloud of gas embedded within the larger structure of the Milky Way. The properties of this cloud, its density, temperature and magnetic field, influence the shape and size of the heliosphere. If the Sun were to move into a denser region of interstellar space, the heliosphere might shrink under the increased pressure. If it entered a more rarefied region, the bubble could expand. Over millions of years, as the Sun orbits the galaxy, the heliosphere may change significantly, though these changes occur far too slowly to notice within a single human lifetime. As Voyager approached the heliopause, scientists watched the data with growing anticipation. They were looking for a clear sign that the spacecraft had crossed into interstellar space. But the crossing did not happen in the way many had expected. Instead of a sudden, unmistakable change, the transition was gradual and complex. Particle counts fluctuated. Magnetic fields behaved in unexpected ways. At times, it seemed as though Voyager had already crossed the boundary, only for new data to suggest that it was still inside. Eventually, however, the evidence became clear. The density of interstellar particles increased sharply, and the intensity of cosmic rays reached levels consistent with interstellar space. Voyager had crossed the heliopause, becoming the first human-made object to enter the space between the stars. It was a quiet milestone. There were no fireworks, no dramatic images, only streams of data arriving at radio antennas on Earth, numbers and graphs that told the story of a crossing billions of kilometers away. Yet the significance of that moment was profound. For the first time, humanity had extended its reach beyond the protective bubble of the Sun. Even so, the heliosphere remains a subject of active research. With only 2 spacecraft sampling its boundary from specific directions, much about its structure is still uncertain. Future missions may one day provide a more complete picture, mapping the heliosphere in detail and revealing how it interacts with the galaxy on a larger scale. For now, Voyager's journey has given us our first direct glimpse of this invisible frontier, turning a theoretical concept into something real, something measured and observed. It has shown us that the boundary of the solar system is not a sharp edge, but a vast and intricate region, shaped by forces both local and galactic. By the time Voyager had passed the last of the giant planets and was heading outward into regions no spacecraft had ever explored, there was a quiet realization among the engineers and scientists following the mission. The spacecraft was still healthy. Its instruments were still working. Its power supply, though slowly declining, was steady. And most importantly, there was still a vast amount of unknown space ahead. In many earlier missions, a spacecraft's journey effectively ended once its primary objectives were completed. After flybys or landings, instruments would be shut down, communication would fade, and eventually the mission would be considered finished. But Voyager was different. It had been built with extraordinary care, designed not only to survive long enough to visit Jupiter and Saturn, but to keep functioning for as long as possible afterward. That decision, made decades earlier by engineers who could only guess how long their machines might last, turned out to be one of the most important in the history of space exploration. Because instead of ending after its planetary tour, Voyager kept going. There is something almost stubborn about that persistence. The spacecraft did not slow down. It did not turn back. It simply continued year after year, moving farther from the Sun at a speed of more than 17 kilometers per second, covering millions of kilometers each day without any engines firing, guided only by the momentum it had gained from planetary flybys long ago. To appreciate how remarkable this is, it helps to consider the distances involved. Even travelling at that speed, Voyager needed years to cross the outer solar system. The scale of space is so vast that motion, which would seem incredibly fast on Earth, becomes, in a sense, patient and gradual when measured against billions of kilometers. Communication with the spacecraft also became more challenging as it travelled outward. Radio signals weaken with distance, spreading out as they travel, and by the time Voyager was tens of billions of kilometers away, its transmissions were incredibly faint. Detecting them required the use of enormous radio antennas on Earth, dishes more than 70 meters across, listening carefully for a signal so weak it carried less power than the electricity used by a small household appliance. Yet even at those distances, the spacecraft continued to respond. Commands sent from Earth, instructions to adjust instruments or change data collection modes, still worked, though each exchange took many hours. Engineers had to plan carefully, anticipating what the spacecraft would need to do long before confirmation could arrive. Another challenge was power. Voyager's radioisotope generators produce electricity from the heat released by the decay of plutonium. This process is steady but gradual, and over time the available power decreases. To extend the mission as long as possible, engineers began turning off instruments that were no longer essential, conserving energy for those that could still provide valuable data about the outer solar system and beyond. Each decision to shut down an instrument was made reluctantly. Every component had been built for a purpose, and many had functioned perfectly for decades. But the goal was to keep the spacecraft alive as long as possible, to allow it to continue its journey into regions no human-made object had ever reached. There is a quiet kind of patience in that process, a sense of stretching time, of carefully managing limited resources so that the mission could continue year after year. As Voyager moved farther from the Sun, the environment around it grew colder and darker. Sunlight at that distance is faint, thousands of times weaker than it is at Earth. The spacecraft's cameras, which had once captured detailed images of planets and moons, were eventually turned off to conserve power. There was little left to photograph anyway. Beyond the outer planets, there are no large objects to see, only the sparse population of distant icy bodies and the endless darkness beyond. Instead of images, Voyager now sends back measurements, data about particles, magnetic fields, and radiation. These numbers may seem less dramatic than photographs, but they tell a story just as profound, revealing the nature of space at the very edge of the sun's influence. One of the most remarkable aspects of Voyager's continued operation is the age of its technology. The spacecraft's computers have less processing power than a modern household appliance. Its memory is measured in kilobytes. The software that guides it was written in an era when programming was done on punch cards and stored on magnetic tape. And yet, despite this simplicity by modern standards, Voyager has proven extraordinarily reliable. Its systems were designed with redundancy, backup components that could take over if primary ones failed. Its instruments were built to withstand radiation, extreme temperatures, and decades of operation without maintenance. Engineers who worked on the mission often speak of the spacecraft with a kind of quiet affection, as if it were not just a machine but a long-lived traveller, continuing its journey long after its creators expected. There is also something deeply human about the way the mission has been sustained. Generations of scientists and engineers have taken turns caring for Voyager, analysing its data, sending commands, and planning its operations. Some of the people who now work on the mission were not yet born when the spacecraft was launched, and yet they are connected across time to those who built it, sharing the same sense of curiosity and dedication. As the spacecraft continued outward, it encountered conditions no one had ever measured before. The solar wind slowed and became turbulent. Cosmic rays increased. Magnetic fields shifted in subtle ways. Each of these changes was a clue, a sign that Voyager was approaching the boundary of the heliosphere. Reaching that boundary was not a single dramatic event, but a gradual process. Data accumulated over months and years, patterns emerging slowly, scientists debating and refining their interpretations, and through it all, Voyager kept going. There is a tendency, when thinking about space missions, to focus on the dramatic moments, the launches, the planetary flybys, the first images of distant worlds. But there is another kind of achievement that is quieter, less visible, yet just as remarkable. It is the achievement of endurance, of continuing long after the initial excitement has faded, of moving steadily forward into the unknown. Voyager embodies that kind of achievement. It is not fast compared to light, not powerful compared to stars, but it is persistent. It continues to move, to measure, to send back whispers of information from regions no one had ever explored before. Even now, decades after its launch, Voyager is still travelling outward. Its power is slowly declining, and eventually, one by one, its instruments will fall silent. But long after the last signal fades, the spacecraft itself will continue drifting through interstellar space, carrying with it the golden record, a small piece of Earth travelling among the stars. There is something quietly moving about the idea that long after our own lifetimes, long after many of the places and cities we know have changed, Voyager will still be out there, a silent traveller crossing the darkness between the stars. But before that distant future arrives, the spacecraft still has more to tell us. As it moved closer to the outer boundary of the heliosphere, the data it transmitted began to reveal something unexpected about the region ahead. Scientists had predicted certain conditions, certain patterns in the particles and magnetic fields, but what Voyager found was not exactly what anyone had imagined. As Voyager continued its steady outward drift, something subtle began to change in the data returning to Earth. At first, it was not dramatic. There were no alarms, no sudden signals announcing that the spacecraft had reached a boundary. Instead, there were small variations, tiny shifts in the behaviour of particles streaming past the instruments, differences so slight that they required careful analysis to notice. For years, scientists had expected that the solar wind would gradually weaken with distance. That part was straightforward. The farther from the sun, the more the stream of charged particles spreads out, becoming thinner and less energetic. But what Voyager began to observe was not simply a steady fading. The solar wind was slowing down in a way that suggested something more complicated was happening ahead. To understand why this mattered, it helps to imagine the solar wind not as a breeze, but as a supersonic flow. Near the Sun, these particles move faster than the speed at which pressure waves can travel through the plasma. In fluid dynamics, when a supersonic flow encounters resistance, it cannot slow down smoothly. Instead, it forms a shock, a sudden transition where speed drops, density increases, and energy is redistributed. This is what scientists believed existed far beyond the planets, a vast region called the termination shock, where the solar wind would slow from supersonic to subsonic speeds as it pushed against the interstellar medium. Theories predicted it. Models suggested where it might be, but until Voyager arrived, no one had ever measured it directly. Long before the spacecraft reached that point, however, hints of the coming change began to appear. Particle detectors showed that the flow of the solar wind was becoming less uniform. Magnetic field measurements revealed fluctuations that were larger and more frequent than before. It was as if the smooth current of a river was beginning to encounter rocks beneath the surface, creating ripples and eddies that disturbed the flow. The scientists studying the data began to realize that Voyager was approaching a region where the solar wind was being affected by conditions beyond the Sun's immediate control. The pressure of interstellar space, though incredibly faint by everyday standards, was beginning to matter. That realization is easier to appreciate if you pause for a moment and consider just how delicate these balances are. The solar wind, even near Earth, is extremely thin, far less dense than the best vacuum chambers we can create on the ground, and yet, over billions of kilometers, the cumulative effect of its pressure is enough to carve out a vast bubble in space. At the same time, the interstellar medium, equally tenuous, exerts its own pressure, pushing inward. Where these two influences meet, a kind of equilibrium forms, and it is in that region that the solar wind begins to slow. Voyager 1 encountered the termination shock in December 2004. The change was unmistakable once it happened. The speed of the solar wind dropped sharply, and the instruments recorded a sudden increase in the density and temperature of particles. It was not a violent event, not something that would have been visible in any ordinary sense, but in the language of data, it was clear and decisive. For the scientist who had spent years anticipating this moment, the confirmation was deeply satisfying. A boundary that had existed only in theory had now been observed directly. The solar system, it turned out, was not simply fading into emptiness. It had structure, layers, regions defined by the physics of plasma and magnetic fields. Yet the story did not end there. Crossing the termination shock was only the beginning of a much longer and more puzzling phase of the journey. Beyond the shock lay the heliosheath, a region where the solar wind, now slowed and heated, continued outward in a more turbulent state. Scientists had expected this region to be complex, but Voyager revealed just how complex it truly was. Instead of a steady flow, the spacecraft encountered variations in particle intensity that rose and fell in unexpected ways. Sometimes the detectors recorded sudden increases in energetic particles, followed by declines that seemed almost rhythmic. Magnetic fields shifted direction more often than predicted. It was as if the spacecraft were moving through a sea filled with currents and whirlpools rather than a uniform stream. One of the most surprising discoveries was how much the solar wind slowed in certain regions. In some measurements, the outward speed of the particles dropped to nearly zero relative to the Sun. This did not mean the spacecraft itself stopped moving, of course. Voyager continued on its trajectory, carried by its own momentum. But the plasma around it seemed to stagnate, as if caught in a kind of cosmic traffic jam where the outward push of the solar wind was nearly balanced by the inward pressure of interstellar space. This phenomenon puzzled researchers. Models had predicted a slowdown, but not such a pronounced one. The idea that the solar wind could nearly stall in some regions suggested that the boundary of the heliosphere was more complex than a simple, smooth shell. It might be wrinkled, folded, or filled with pockets, where the flow behaved differently depending on local conditions. Another unexpected finding involved energetic neutral atoms, particles created when charged particles exchange electrons with neutral atoms drifting in from interstellar space. These neutral atoms can travel long distances without being affected by magnetic fields, carrying information about regions far beyond the spacecraft itself. Measurements of these particles provided indirect clues about the structure of the heliosphere and the processes occurring at its boundary. As the data accumulated, scientists began to realize that the heliosheath was not just a transition zone, but a dynamic environment shaped by waves, shocks, and interactions on scales that were difficult to imagine. The solar wind, once thought of as a steady outward flow, was revealed to be far more variable and complex when observed at such great distances. There was also the question of timing. Changes in the solar wind observed near Earth take years to propagate outward to the distances where Voyager was travelling. This meant that the spacecraft was encountering conditions shaped by solar activity that had occurred long before. In a sense, it was moving through layers of history, each region reflecting the state of the Sun years earlier. This introduced another layer of complexity in interpreting the data. Scientists had to consider not only where Voyager was, but also what the Sun had been doing years before, reconstructing a timeline that linked events near Earth with conditions billions of kilometers away. Communication delays added to the sense of distance and patience required. By this stage, signals took more than half a day to travel one way. Data arriving on Earth represented conditions that had already changed by the time scientists began analysing them. The mission unfolded on timescales that required a different kind of thinking, slower, more deliberate, more reflective. Meanwhile, Voyager 2, following a different path through the outer solar system, encountered the termination shock in 2007 at a slightly closer distance to the Sun than Voyager 1 had. This difference provided an important clue. The heliosphere was not symmetrical. Its boundary varied depending on direction, influenced by the interstellar magnetic field and the motion of the Sun through the galaxy. The idea that the solar system's outer boundary was uneven and dynamic changed the way scientists thought about it. Instead of a neat spherical bubble, the heliosphere appeared more like a shifting, irregular structure, shaped by forces both internal and external. Another intriguing observation was the behaviour of cosmic rays. As Voyager moved deeper into the heliosheath, the intensity of these high-energy particles increased steadily. This was expected since the shielding effect of the solar wind weakens near the boundary. But the rate of increase and the patterns observed were more complicated than predicted, suggesting that the heliosphere filters cosmic rays in ways that are not yet fully understood. All of these discoveries contributed to a growing sense that the edge of the Sun's influence was not a simple frontier, but a region of subtle and fascinating physics. The slowdown of the solar wind was not just a mechanical effect, but part of a larger story about how stars interact with the galaxy around them. It is worth pausing for a moment to consider what this means on a broader scale. Every star in the Milky Way produces its own stellar wind, creating a bubble of influence in the surrounding interstellar medium. These bubbles, or astrospheres as they are sometimes called, may overlap, interact, and evolve over time. By studying the heliosphere, we're not only learning about our own solar system, but also gaining insight into the environments around other stars. Voyager's journey, then, is not just about one spacecraft or one boundary. It is part of a larger effort to understand how stars shape the space around them, how cosmic rays propagate through the galaxy, and how the delicate balance of pressures and fields defines the regions where planets and, perhaps, life can exist. As the spacecraft continued through the heliosheath, the signs that it was approaching the heliopause grew stronger. The solar wind slowed further, cosmic rays increased, and the density of interstellar particles began to rise. Each new measurement brought scientists closer to answering a question that had lingered for decades. Where exactly does the Sun's influence end? There was no flash of light, no sudden jolt, no visible sign that anything dramatic had happened. Voyager did not cross a glowing line or pass through a curtain of stars. From the spacecraft's perspective, the surroundings looked much the same as they had the day before and the day before that. Space remained dark, cold, and silent, and yet, at some point in 2012, Voyager 1 quietly became the first human-made object to enter interstellar space. What makes that moment remarkable is how subtle it was. The boundary between the heliosphere and interstellar space, the heliopause, is not something that can be seen with a camera. It is defined by changes in particles and magnetic fields, by shifts in invisible conditions that only sensitive instruments can detect. For the scientists watching the data, the crossing was not announced by a single measurement, but revealed gradually, piece by piece, as patterns emerged over weeks and months. To understand what happened, it helps to recall what the heliopause represents. Inside it, the solar wind dominates. Outside it, the interstellar medium becomes the controlling environment. The transition is governed by pressure, by the balance between the outward push of the sun's particles and the inward pressure of the gas and magnetic fields that drift between the stars. As Voyager approached this boundary, its instruments began recording signs that the balance was shifting. One of the clearest indicators came from cosmic rays. These high-energy particles, many of them accelerated by distant supernova explosions, are partially deflected by the heliosphere. Near Earth, their intensity is lower than it is in interstellar space because the solar wind acts as a kind of shield. But in 2012, Voyager's detectors recorded a sharp increase in cosmic ray intensity, far greater than anything seen before during the mission. At the same time, the number of lower energy particles associated with the solar wind dropped dramatically. It was as if one population of particles was fading away while another surged in to replace it. This was one of the first strong hints that Voyager had crossed into a new region. Still, scientists were cautious. Data from the heliosheath had already shown that conditions near the boundary could fluctuate. Temporary changes could mimic a crossing, only to reverse days or weeks later. So, they waited. More data arrived. The pattern held. The intensity of cosmic rays remained high, and the solar wind particles remained scarce. Something fundamental had changed in the environment around the spacecraft. Another important clue came from plasma waves. Voyager carried an instrument capable of detecting oscillations in the surrounding plasma, tiny vibrations that reveal the density of charged particles. In interstellar space, the plasma density is expected to be higher than in the outer heliosphere. For years, Voyager had not been able to measure this directly, because the plasma wave instrument relied on occasional disturbances, such as shock waves from solar eruptions, to produce detectable signals. In 2013, such a disturbance passed the spacecraft, creating oscillations that allowed scientists to measure the plasma density for the first time. The result was unmistakable. The density matched what was expected for interstellar space, not the heliosphere. It was like hearing a distant echo that confirmed you had entered a different landscape. There was also the magnetic field. Scientists had expected that crossing the heliopause would involve a noticeable change in the direction of the magnetic field, since the interstellar field is oriented differently from the Sun's. Surprisingly, this change was smaller than predicted. The field strength increased, but its direction remained similar, suggesting that the boundary was more complex than a simple dividing line. This unexpected finding sparked intense discussion. Some researchers wondered whether Voyager had truly crossed the heliopause or was in a transitional region. Over time, however, the combined evidence from particle counts, plasma density, and magnetic field measurements made the conclusion clear. Voyager was in interstellar space. The moment of realization was not dramatic in the way one might imagine. There was no single day when scientists gathered to watch a screen and cheer as a line was crossed. Instead, there was a gradual recognition, built on careful analysis, that humanity had reached a milestone that had once seemed almost unreachable. It is worth pausing to consider what this means in practical terms. Voyager is now travelling through material that did not originate in our solar system. The particles around it were born in distant stars, in clouds of gas that drift through the galaxy, in shock waves from explosions that occurred long before the sun itself formed. For billions of years, our solar system has been moving through this interstellar environment, surrounded by it, shaped by it, yet separated from it by the heliosphere. Now, for the first time, a human-made object is directly sampling that environment, measuring its properties, and sending the results back across immense distances. Even the communication itself feels extraordinary when you think about it. The signals Voyager transmits travel at the speed of light, yet they take more than 20 hours to reach Earth. By the time scientists receive the data, it is already nearly a day old. A message from a spacecraft so distant that its radio transmitter, powered by a diminishing source of electricity, produces only a faint whisper detectable by the largest antennas on our planet. And still, that whisper carries knowledge that could not be obtained any other way. The crossing of the heliopause also changed the way scientists think about the boundary of the solar system. It confirmed that the heliosphere does indeed act as a shield, reducing the intensity of cosmic rays in the inner regions. It provided direct measurements of interstellar plasma density, magnetic fields, and particle populations, turning theoretical models into observed reality. Perhaps most importantly, it revealed that the boundary is not simple. The heliopause is not a sharp wall, but a complex region influenced by magnetic fields, turbulence, and variations in both the solar wind and the interstellar medium. The expectations scientists had built over decades were refined, adjusted, and in some cases overturned by the data Voyager sent back. Voyager 2, following a different path through the solar system, crossed the heliopause in 2018, providing a second set of measurements that confirmed and expanded upon what Voyager 1 had observed. The differences between the two crossings showed that the heliosphere's boundary varies depending on direction, shaped by conditions that are not uniform around the Sun. These discoveries may seem subtle compared to images of planets or galaxies, but they are profound in their own way. They tell us where our star's influence ends, how it interacts with the galaxy, and what conditions are like in the vast regions between stars. There is also something quietly humbling about the idea that the first step into interstellar space was taken not by a crude spacecraft, not by a grand vessel carrying people, but by a small, silent probe launched decades ago, continuing its journey long after its primary mission had ended. Voyager did not set out with the explicit goal of crossing the heliopause. That milestone was reached because the spacecraft endured, because it kept working, because the people guiding the mission chose to keep listening, keep analysing, keep asking questions. Even now, as it travels farther into interstellar space, Voyager continues to send back data, though the available power decreases each year. Instruments are turned off one by one to conserve energy, extending the mission for as long as possible. Eventually, sometime in the coming decade, the spacecraft will fall silent. But long after the last signal fades, Voyager will continue drifting among the stars, carrying with it the golden record, a silent testament to the curiosity of the species that built it. For the scientists who study the data, however, the story is far from over. The measurements Voyager has already provided are still being analysed, still revealing new insights about the boundary of the heliosphere and the nature of interstellar space. And as those insights accumulate, one thing has become clear. The region beyond the heliopause is not as simple as anyone once imagined. The particles, fields, and structures Voyager encountered there behaved in ways that challenged expectations and raised new questions about how stars interact with their galactic surroundings. What made the crossing of the heliopause so surprising was not simply that Voyager reached it. Scientists had expected that moment for years. They had built models, run simulations, and debated where the boundary might lie. The surprise came from what the spacecraft actually measured once it arrived. and from how different reality turned out to be compared with those expectations. For decades, researchers had tried to picture what the outer boundary of the heliosphere would be like. Most imagined a fairly clear transition. Inside the heliosphere, the solar wind would dominate. Outside it, interstellar space would take over. There might be turbulence near the boundary, of course, but the overall structure seemed straightforward in theory. Yet space, as it often does, turned out to be more complicated. One of the first surprises involved the magnetic field. Before Voyager reached the heliopause, many scientists believed that the direction of the magnetic field would change noticeably when the spacecraft crossed into interstellar space. The Sun's magnetic field, carried outward by the solar wind, follows a spiral pattern caused by the Sun's rotation. The interstellar magnetic field, by contrast, was expected to have a different orientation. So when Voyager approached the boundary, researchers were watching closely for a sudden shift in the direction of the magnetic field lines. That shift, they thought, would be one of the clearest indicators that the spacecraft had left the Sun's domain. But the change was far smaller than predicted. The strength of the magnetic field increased, which suggested that Voyager had indeed entered a denser and more compressed region. But the direction of the field remained surprisingly similar to what it had been inside the heliosphere. This puzzled scientists. It suggested that the boundary between the heliosphere and interstellar space was not a clean separation of two distinct magnetic environments. Instead, the fields appeared to interact, to drape and twist around each other in ways that smoothed out what had been expected to be a sharp transition. That realization forced researchers to rethink their understanding of how the heliosphere interacts with the galaxy. The boundary was not a simple dividing line. It was a region of mixing, compression, and complex magnetic behavior that models had not fully captured. Another surprise involved the density of interstellar plasma. For many years, estimates of the plasma density outside the heliosphere were based on indirect observations and theoretical calculations. Voyager provided the first direct measurements, and they showed that the density was higher than many scientists had expected. This finding had important implications. A higher plasma density affects how waves travel through interstellar space, how cosmic rays propagate, and how the heliosphere itself is shaped by external pressure. It also suggested that the region of the galaxy through which the Sun is currently moving, sometimes called the local interstellar cloud, may have properties different from what earlier models had assumed. There was also the behavior of cosmic rays. Scientists had long known that the heliosphere acts as a shield, reducing the intensity of these high-energy particles in the inner solar system. As Voyager approached the heliopause, the intensity of cosmic rays increased, just as expected. But the rate and pattern of that increase were more complex than predicted. Instead of a smooth, gradual rise, the data showed fluctuations, sudden jumps, and periods of relative stability. It was as if the boundary region contained structures that influenced how cosmic rays moved, regions where particles were temporarily trapped or deflected before continuing on their paths. These patterns revealed that the heliopause is not just a passive boundary, it is an active region, where particles and magnetic fields interact in ways that can shape the flow of radiation through the solar system. The heliosheath, the region just inside the heliopause, also turned out to be more turbulent and variable than expected. Voyager detected changes in particle intensity that suggested the presence of waves and structures moving through the plasma. Some researchers compared it to weather patterns in the atmosphere, not in the sense of clouds or rain, but in the sense of a dynamic environment where conditions change over time rather than remaining constant. One particularly intriguing discovery involved the near stagnation of the solar wind in certain regions. Models had predicted that the solar wind would slow as it approached the heliopause, but Voyager observed areas where the outward flow of particles was almost completely halted. This was surprising because it suggested that the balance of forces at the boundary was more delicate and more variable than expected. Instead of a steady outward flow meeting, a steady inward pressure, the interaction appeared to involve shifting regions where the motion of plasma could change dramatically over relatively short distances. Another unexpected result came from the shape of the heliosphere itself. Earlier models often depicted it as comet-like, with a rounded front and a long tail trailing behind as the sun moves through the galaxy. But data from Voyager, combined with observations from other missions that study energetic neutral atoms, suggested that the heliosphere might be more rounded, or even somewhat squashed, rather than stretched into a long tail. This remains an area of active research, but the key point is that the structure of the heliosphere is influenced by many factors, including the interstellar magnetic field, the pressure of interstellar gas, and variations in the solar wind over time. The boundary Voyager crossed is part of a much larger and more complex system than anyone had fully realized. There was also a psychological aspect to the surprise. For many years, the heliosphere had been an abstract concept, something discussed in papers and conferences but never directly experienced. Voyager turned it into a place, a region with measurable properties, a frontier that could be crossed. And when that crossing happened, it revealed that the models scientists had relied on were only approximations. They had captured some aspects of reality, but not all. The boundary was more irregular, more dynamic, and more subtle than expected. This is not unusual in science. When new regions are explored for the first time, whether the deep ocean, the polar regions, or distant planets, reality often turns out to be more complex than the simplified pictures drawn beforehand. Voyager's journey was no exception. There was also something quietly astonishing about the fact that these discoveries were being made by a spacecraft launched in 1977. The instruments on Voyager were designed decades before it reached interstellar space, yet they were still capable of providing measurements that reshaped our understanding of the solar system's boundary. This speaks not only to the skill of the engineers who built the spacecraft, but also to the foresight of the scientists who decided to include instruments capable of studying regions that, at the time of launch, seemed unimaginably distant. Another reason the crossing was so significant is that it provided the first direct sample of interstellar space. Before Voyager, most of what we knew about the interstellar medium came from observations of light, spectroscopy, and indirect measurements. Voyager allowed scientists to measure the local interstellar environment directly, to detect particles and fields in situ, rather than inferring their properties from afar. This is a bit like the difference between studying the ocean by looking at waves from the shore and actually lowering instruments into the water. Both approaches are valuable, but direct measurement provides a level of detail and certainty that cannot be obtained in any other way. The discoveries Voyager made also have broader implications for our understanding of other planetary systems. Many stars are surrounded by astrospheres, bubbles created by stellar winds interacting with interstellar space. By studying our own heliosphere, scientists gain insight into how these structures might behave around other stars, including those that host planets. This has implications for cosmic radiation, for the environments of distant worlds, and even for the conditions that might affect the development of life. The heliosphere, in shielding the inner solar system from some cosmic rays, may play a role in shaping the radiation environment of Earth and other planets. Understanding how such shielding works helps us understand what conditions might be like in other star systems. There was also an emotional dimension to the moment. For the people who had spent their careers studying Voyager, the crossing of the heliopause was the culmination of decades of work. Some of the original mission team were still alive to see it, though many had retired. Younger scientists who had grown up hearing about Voyager were now analysing its data and contributing to discoveries that connected them to a mission older than they were. It created a sense of continuity, of knowledge passed from one generation to the next, carried forward just as the spacecraft itself carried forward through space. Even now, years after the crossing, the data Voyager continues to send back is being analysed, revealing new details about the interstellar medium and the boundary of the heliosphere. Each measurement adds another piece to the puzzle, helping scientists refine their models and understand the processes that shape the space between stars. Perhaps the most profound realization of all is how thin and fragile the heliosphere is on a cosmic scale. It feels vast to us, stretching more than 100 astronomical units from the Sun. But compared to the distances between stars, it is a tiny bubble. The galaxy is filled with such bubbles, each created by a star, each interacting with its surroundings in ways we are only beginning to understand. Voyager's journey has shown us that even the most familiar structures, like the solar system itself, can hold surprises when examined closely. The edge of the Sun's influence is not a simple frontier, but a region of complexity and subtlety, shaped by forces that operate across immense distances. For a long time, the outer boundary of the solar system was imagined in a very simple way. Scientists pictured the heliosphere as something like a comet, rounded at the front where the solar wind pushes against the interstellar medium, and stretched into a long tail behind, shaped by the motion of the Sun through the galaxy. It was a reasonable assumption. After all, we see similar shapes in many other situations. A boat moving through water leaves a wake behind it. A gust of wind shapes smoke into a trailing plume. It seemed natural that the Sun, moving through interstellar space, would create a long, streaming tail of solar wind extending far into the distance. Yet the more data scientists gathered, the more that tidy picture began to soften and blur. Voyager's measurements were only one part of the story. Other spacecraft closer to Earth, studying energetic neutral atoms, began to provide a broader view of the heliosphere, revealing patterns that did not quite match the classic comet-like shape. To understand how scientists began to rethink the frontier of the solar system, it helps to consider how difficult it is to observe something so vast and invisible. The heliosphere cannot be photographed directly. It does not glow or reflect light in a way telescopes can easily detect. Instead, researchers must rely on indirect methods, studying particles and radiation that carry information about distant regions. One of the most useful of these methods involves energetic neutral atoms, or ENAs. These particles form when charged particles from the solar wind exchange electrons with neutral atoms drifting in from interstellar space. Once neutral, they are no longer guided by magnetic fields and can travel in straight lines across great distances. By detecting these particles and tracing their directions, scientists can create maps that reveal structures far beyond the reach of spacecraft. When these maps were first produced, they showed something unexpected. Instead of a long, narrow tail trailing behind the Sun, the heliosphere appeared more rounded, and in some interpretations even divided into two broad lobes rather than one extended stream. Some researchers compared the shape to a croissant, with two curved regions extending behind the Sun rather than a single elongated tail. This was surprising, not only because it challenged earlier models, but also because it suggested that magnetic fields play a much larger role in shaping the heliosphere than previously thought. The Sun's magnetic field, carried outward by the solar wind, interacts with the interstellar magnetic field in complex ways, twisting and redirecting flows of plasma. These interactions can prevent the solar wind from stretching into a long tail, instead channeling it into broader, more structured regions. Voyager's measurements added another piece to the puzzle. The spacecraft crossed the heliopause in different directions, and the distances at which they encountered key boundaries were not the same. Voyager 1 crossed the heliopause at about 121 astronomical units from the Sun, while Voyager 2 crossed at roughly 119 astronomical units, and the conditions they measured were not identical. This told scientists that the heliosphere is not perfectly symmetrical. Its boundary shifts depending on direction, influenced by variations in the solar wind and by the properties of the interstellar medium. There is something quietly fascinating about this idea. We often think of the solar system as centered on the Sun, with everything arranged neatly around it. But in reality, the Sun is moving through the galaxy, and the environment around it is not uniform. The interstellar medium has its own structure, its own magnetic fields, its own subtle currents of particles. The heliosphere forms where these influences meet, and its shape reflects that interaction. Another factor complicating the picture is time. The solar wind is not constant. The sun goes through cycles of activity, roughly every 11 years, during which the intensity of the solar wind and the strength of the sun's magnetic field change. These variations propagate outward over years and decades, altering the shape and size of the heliosphere. This means that the frontier of the solar system is not fixed. It expands and contracts slowly, like a breathing bubble, responding to changes in the sun and in the interstellar medium. A spacecraft crossing the boundary at one time may encounter different conditions than one crossing years later, even along a similar path. There is also the influence of turbulence. The boundary region between the solar wind and interstellar space is not smooth. Voyager detected fluctuations in particle densities and magnetic fields that suggested the presence of waves and instabilities. These features can ripple through the heliopause, creating irregularities that make the boundary uneven and dynamic. If it were possible to see the heliosphere from a great distance, it might appear less like a perfect bubble and more like a living structure, constantly shifting, its surface rippling and reshaping under the influence of forces both internal and external. Understanding this structure is not just an academic exercise. The shape of the heliosphere affects how cosmic rays enter the solar system, how interstellar particles interact with the solar wind, and how the environment around our star evolves over time. It also provides insight into similar structures around other stars, helping astronomers understand how stellar winds shape the regions where planets form and exist. One of the most intriguing aspects of this research is how it combines data from very different sources. Voyager provides in situ measurements, direct observations of conditions at specific points far from the Sun. Missions closer to Earth, such as those studying energetic neutral atoms, provide global maps that reveal larger structures. Computer simulations bring these pieces together, allowing scientists to test different models and see which ones best match the observations. This process takes time. Models are refined, new data arrives, and interpretations evolve. The picture of the heliosphere's shape is still changing, becoming more detailed and more nuanced with each passing year. There is a certain patience in this kind of work, a recognition that understanding vast and subtle structures requires careful accumulation of evidence. Voyager's journey, spanning decades, is perfectly suited to this task. It provides a long, continuous record of measurements, revealing changes that occur slowly, over years rather than minutes. Another realization that emerged from these studies is how small the heliosphere is compared to the galaxy. Even at its largest extent, it is only a tiny bubble in a vast ocean of interstellar space. The nearest star lies thousands of times farther away than the heliopause. From a galactic perspective, the solar system's frontier is a delicate, localized feature, a temporary structure shaped by the interplay of stellar and interstellar forces, and yet for us it is immensely significant. Inside that bubble lies every planet, every asteroid, every comet we have ever observed directly. It is the environment in which Earth formed and in which life evolved. Understanding its shape and behaviour is part of understanding our own origins and our place in the galaxy. Voyager's role in this discovery cannot be overstated. Without direct measurements from the outer heliosphere, many of these ideas would remain speculative. The spacecraft's data provide anchor points, real observations that guide and constrain theoretical models. There is also something quietly inspiring about the way this knowledge has been gathered. It has not come from a single dramatic event, but from years of steady observation, careful analysis, and collaboration among scientists around the world. The shape of the solar system's frontier has emerged gradually, like a coastline revealed by the slow lifting of fog. As researchers continue to study the heliosphere, new questions arise. How does its shape change as the Sun moves through different regions of the galaxy? How does the interstellar magnetic field influence its structure? What happens when the heliosphere encounters denser clouds of interstellar gas, as it likely has in the distant past and will again in the distant future? These questions remind us that the solar system is not isolated. It is part of a larger environment, moving through the Milky Way, interacting with the galaxy in subtle but important ways. The heliosphere is the boundary of that interaction, the frontier where the influence of our star meets the influence of the wider cosmos. And beyond that frontier lies a region that, for most of human history, existed only in imagination, the space between the stars themselves. Voyager has begun to explore that region, sending back data that reveal its properties in ways never before possible. Far beyond the heliopause, the environment around Voyager changed in a way that is difficult to picture at first. Inside the heliosphere, most of the particles surrounding the spacecraft had originated from the Sun. They were part of the solar wind, born in the hot outer atmosphere of our star and carried outward across billions of kilometres. But once Voyager crossed that invisible boundary, the majority of the particles it encountered were no longer solar in origin. They had come from somewhere else, from the vast regions between stars, from events and processes scattered across the Milky Way over immense stretches of time. It is tempting to think of interstellar space as empty, a kind of perfect vacuum where nothing exists. The word space itself encourages that image, yet the reality is more subtle. Interstellar space is thin beyond ordinary comprehension, far less dense than the best vacuum chambers ever built on Earth. But it is not nothing. It contains atoms, eons, electrons, dust grains, and high-energy particles drifting slowly through the galaxy. These components form what astronomers call the interstellar medium. Voyager is now travelling through a part of this medium known as the local interstellar cloud, a region of warm, sparse gas that surrounds our solar system. The density of this cloud is extraordinarily low by everyday standards. In a cubic centimetre of air at sea level on Earth, there are about 10 quintillion molecules. In the interstellar medium, there may be only a fraction of an atom in that same volume. And yet, across the vastness of space, even such tenuous material becomes significant. Over distances of trillions of kilometres, it accumulates, interacts, and shapes the environments of stars and planets. One way to imagine this is to think of a vast ocean so thin that each drop is separated from the next by kilometres of empty space, yet still forming a continuous medium on the larger scales. Voyager is drifting through that ocean now, carried forward by the momentum it gained decades ago, surrounded by particles that may have been travelling for millions of years before ever encountering the spacecraft. Some of these particles are simple hydrogen atoms, the most abundant element in the universe, remnants of ancient cosmic processes. Others are helium, or traces of heavier elements forged in the cores of stars and scattered into space by stellar winds and supernova explosions. There are also dust grains, tiny fragments of carbon and silicates, smaller than grains of smoke, drifting silently through the darkness. And then there are cosmic rays, among the most energetic particles known, travelling at nearly the speed of light. Many of them were accelerated by shock waves from exploding stars long ago. Some may have begun their journeys before our solar system even formed. By the time they reach Voyager, they carry with them a history written not in words but in energy, direction, and composition. Inside the heliosphere, the solar wind and the sun's magnetic field deflect many of these cosmic rays, reducing their intensity. But beyond the heliopause, that shielding is much weaker. Voyager's instruments detected a noticeable increase in cosmic ray intensity after the crossing, confirming that the spacecraft had entered a region where the influence of the galaxy outweighed that of the Sun. This increase was not just a scientific curiosity. It was a direct measurement of the environment that exists between stars, a region that, until Voyager arrived, had been studied only indirectly. Another important aspect of the interstellar medium is its temperature. Despite the darkness and distance from stars, some regions of interstellar space are surprisingly warm. The local interstellar cloud, for example, has a temperature of several thousand degrees Celsius. That may sound intense, but temperature in such a thin medium does not mean what it does on Earth. Temperature is a measure of the average energy of particles, not how hot something would feel to the touch. In a gas so sparse, there are too few particles to transfer heat effectively. A thermometer placed there would not warm in the way it would in a hot room, because there would be almost nothing to conduct energy to it. Voyager's instruments do not measure temperature directly in the way a household thermometer does, but they can infer it by analysing the motion and energy of particles. These measurements confirmed that interstellar space is not a uniform, featureless void. It has structure, temperature, density, and magnetic fields that vary from place to place. Magnetic fields in particular play a subtle but important role in shaping the interstellar medium. Though extremely weak compared to magnets on Earth, these fields extend across vast distances, guiding the motion of charged particles and influencing the formation of clouds and stars. Voyager detected changes in magnetic field strength and orientation that provided clues about the larger structure of the galaxy in our region. It is remarkable to consider that a spacecraft smaller than a compact car, launched in the 1970s, is now measuring properties of the galaxy itself, sampling the conditions of a medium that fills the space between billions of stars. The silence of this region is another striking aspect. There is no air to carry sound, no wind in the familiar sense, no waves breaking on a shore, and yet in a way interstellar space is not entirely silent. The particles and fields within it interact, creating oscillations and waves in the plasma, vibrations that Voyager can detect with its instruments. These are not sounds as we normally experience them, but they can be translated into audio frequencies, allowing us to hear the environment of interstellar space in a form our senses can grasp. Before we come to those strange and haunting signals, it is worth lingering a little longer on the nature of this silent ocean through which Voyager is travelling. Distances in interstellar space are so vast that even at Voyager's speed, it would take tens of thousands of years to approach another star. The spacecraft is moving quickly by human standards, faster than any airplane, faster than any bullet, yet the scale of the galaxy makes that speed seem almost gentle. If Voyager were aimed toward the nearest star, Proxima Centauri, and continued at its current speed, it would take more than 70,000 years to arrive. That is longer than all of recorded human history. Entire civilizations rise and fall in shorter spans of time. Languages change, continents shift, species evolve, and still the spacecraft would be on its way, drifting steadily through the darkness. This perspective helps to explain why the interstellar medium feels so vast and so quiet. Events are separated by enormous distances and timescales. A particle detected by Voyager today may have travelled for millions of years without encountering anything larger than a dust grain. And yet, even in that quiet, there is motion. The local interstellar cloud itself is drifting relative to the Sun. The Sun, in turn, is orbiting the centre of the Milky Way, carrying the heliosphere and its planets with it on a journey that takes hundreds of millions of years to complete a single circuit. Voyager is part of that motion now, no longer sheltered within the Sun's bubble, but exposed to the broader environment of the galaxy. Its instruments are sampling particles that may have originated in distant stellar nurseries, in shock waves from ancient supernovae, or in clouds of gas that will one day collapse to form new stars. There is something quietly profound about that connection. The atoms and particles drifting past Voyager are part of the same cosmic cycle that created the Sun, the Earth, and every living thing. Hydrogen formed in the earliest moments of the universe. Heavier elements were forged in stars and scattered into space. Over billions of years, that material gathered into new stars and planets, including our own world. Now, as Voyager travels through the interstellar medium, it is surrounded by the raw material of future solar systems, the building blocks of stars and planets yet to form. Even the dust grains drifting through this region tell a story. Some are coated with ices, others with complex organic molecules formed in cold molecular clouds. These tiny particles, almost unimaginably small, play a role in the chemistry of the galaxy, providing surfaces where atoms can combine to form new molecules. It is a reminder that space is not static. It is not merely a backdrop for stars and planets. It is an active environment, a medium through which energy and matter flow, a place where processes unfold slowly but continuously over immense spans of time. Voyager's measurements of this environment are still being analysed, still contributing to our understanding of the galaxy. Each bit of data helps refine models of cosmic ray propagation, interstellar chemistry, and the interaction between stellar winds and the interstellar medium. There is also a human dimension to this story. The signals Voyager sends back are faint, requiring sensitive receivers and careful processing to detect. Teams of scientists and engineers continue to monitor the spacecraft, interpreting its data, adjusting its operations, and preserving the flow of information for as long as possible. One day, the power available to Voyager will drop below the level needed to operate its transmitters. The spacecraft will fall silent, still travelling, still surrounded by the silent ocean of interstellar particles, but no longer able to send messages home. Even then, it will continue its journey, orbiting the centre of the galaxy along with the Sun and countless other stars, a tiny artifact of a small planet drifting through a medium that existed long before humanity and will continue long after. For now, though, Voyager is still speaking, still measuring, still revealing details about the interstellar medium that no other instrument has ever observed directly. Not long after Voyager entered interstellar space, scientists began noticing something unusual in the data from one of its instruments. It was not an image, not a particle count, not a magnetic reading in the usual sense. It was a pattern, a set of faint oscillations in the plasma surrounding the spacecraft. Vibrations so subtle that at first they were easy to overlook. These oscillations were not sound in the way we normally think of it. There is no air in interstellar space, no medium dense enough to carry sound waves that human ears could detect. Yet plasma, a gas of charged particles, can support waves of its own, disturbances that ripple through it, compressing and rarefying the particles in ways that can be measured electronically. Voyager carried a plasma wave instrument designed to detect exactly these kinds of vibrations. For many years, while the spacecraft was still inside the heliosphere, the instrument had recorded similar signals, often triggered by shock waves travelling outward from solar eruptions. These events would briefly disturb the plasma, creating oscillations that allowed scientists to measure the density of particles in regions far from the Sun. But beyond the heliopause, the character of these signals began to change. The first clear detection came when a powerful eruption on the Sun sent a shock wave racing outward through the heliosphere. It took more than a year for that disturbance to reach Voyager's position, and when it did, it compressed the interstellar plasma around the spacecraft, causing it to vibrate. The plasma wave instrument recorded the oscillations, and from their frequency, scientists were able to calculate the density of the surrounding medium. That measurement was one of the key confirmations that Voyager was truly in interstellar space. But what captured the imagination of many people was what happened next, when researchers converted those oscillations into audible frequencies. By shifting the frequencies into the range of human hearing, they created a recording that sounded like a rising ghostly tone, a kind of distant whistle or hum. It was not music, not exactly noise, but something in between, a sound shaped by the properties of a medium that exists far beyond the reach of our senses. Hearing it for the first time was a strange experience. It was, in a sense, the sound of interstellar space itself, or at least the sound of its plasma vibrating in response to a passing shock wave. A sound from billions of kilometers away, carried not through air but through data, translated by instruments and computers into something our ears could understand. There is something quietly powerful about that idea. For most of human history, the space between stars was imagined as completely silent, utterly empty. And in everyday terms it still is silent, but at a deeper level it is filled with subtle motions, waves and vibrations, patterns that can be detected and, with a bit of interpretation, even heard. The frequencies Voyager recorded were determined by the density of the plasma. Higher densities produce higher frequency oscillations, while lower densities produce lower ones. By analysing these frequencies, scientists could measure how the density of the interstellar medium changed over time as the spacecraft moved through it. These measurements revealed that interstellar space is not perfectly uniform. The density of particles varies, sometimes gradually, sometimes more abruptly, suggesting the presence of structures within the local interstellar cloud. These structures are far too diffuse to be seen directly, but they are real, and Voyager's instruments provide one of the few ways to study them. It is interesting to consider what these plasma waves would be like if we could somehow experience them directly. They would not resemble the sounds we hear on Earth. There would be no echoes, no reverberations from walls or surfaces, no familiar acoustic textures. The waves would propagate through a medium so thin that their energy would be extraordinarily faint, far below the threshold of human hearing. And yet, when translated into sound, they carry a kind of quiet beauty, a reminder that even the most remote regions of the universe are not completely still. The origin of these waves is also fascinating. Many of them are triggered by events that occur far away, sometimes at the sun itself. A solar eruption sends a shock wave outward, travelling for months or years across the heliosphere and into interstellar space. When it reaches Voyager, it compresses the plasma, creating oscillations that the spacecraft can detect. In this way, the Sun continues to influence Voyager's environment even after the spacecraft has left the heliosphere. The disturbances it produces propagate outward like ripples on a pond, crossing vast distances before finally reaching the spacecraft. There is something remarkable about the timescales involved. An eruption that occurs on the Sun today might not affect Voyager until years later. By the time the resulting data reaches Earth, the total delay, from eruption to detection to transmission, can span a significant portion of a human lifetime. This slow unfolding of events gives the mission a different rhythm from most scientific experiments. It is not a matter of seconds or minutes, but of months and years of patient observation and careful analysis. The plasma wave instrument itself is a relatively simple device compared to some of the more complex instruments carried by modern spacecraft. Yet its simplicity is part of its strength. Designed decades ago, it has continued to operate reliably, detecting signals so faint that they would be lost in the noise of most terrestrial environments. One of the challenges in interpreting these signals is distinguishing between waves generated locally and those arriving from distant disturbances. Scientists must analyze the patterns carefully, comparing them with models and with data from other spacecraft to determine their origins. Over time, a picture has begun to emerge of interstellar space as a medium filled with subtle activity. Plasma waves propagate through it. Magnetic fields twist and shift. Cosmic rays pass through, occasionally interacting with atoms and ions. Dust grains drift slowly, influenced by electromagnetic forces. None of this is dramatic in the way we often imagine space phenomena to be. There are no blazing explosions nearby, no brilliant nebulae glowing in the darkness. Instead, there is a quiet, persistent motion, a kind of background activity that continues whether anyone observes it or not. Listening to the translated sounds of these plasma waves can create an unusual sense of connection. The tones are faint and distant, yet they represent real physical processes occurring far beyond the reach of human travel. They are echoes of shock waves, signatures of particle densities, whispers of the interstellar medium. It is also worth remembering that these sounds are not artificial in the sense of being invented or simulated. They are derived directly from measurements, from the oscillations of charged particles around a spacecraft billions of kilometers away. What we hear is a representation of reality, translated into a form our senses can grasp. There is a long tradition in science of converting data into sound. Astronomers have transformed the vibrations of stars, the emissions of pulsars, and the signals from planetary atmospheres into audio, revealing patterns that are sometimes easier to perceive by ear than by eye. The sounds of interstellar plasma are part of that tradition, offering a new way to experience environments that are otherwise inaccessible. For the engineers and scientists who work with Voyager's data, these sounds are more than curiosities. They are tools providing precise information about plasma densities and shock wave propagation. Each oscillation carries quantitative meaning, allowing researchers to calculate conditions in regions that no spacecraft had ever sampled before. And yet, beyond their scientific value, they also have a kind of quiet, emotional resonance. Hearing them, it is hard not to think about the distance involved, the decades of travel, the fragile chain of technology and human effort that makes such measurements possible. Voyager itself, drifting through the interstellar medium, continues to detect these waves from time to time, each one a reminder that space is not entirely silent, that even in the darkness between stars there is motion and energy and change. As the spacecraft moves farther from the sun, the signals grow weaker, the available power declines and the intervals between measurements lengthen, but the mission continues, sustained by careful management and the dedication of the people who monitor it. There is a certain patience required to appreciate discoveries like these. They do not arrive with dramatic images or sudden revelations. They emerge gradually, from faint signals and subtle patterns, from years of observation and analysis. And perhaps that is fitting, because the environment Voyager is exploring is itself a place of slow processes and gentle motions, where change occurs over immense spans of time and distance. Long before Voyager ever reached the outer boundary of the heliosphere, scientists already knew about cosmic rays, but their true nature and behaviour were still full of mysteries. These particles, travelling at enormous speeds, had been detected on Earth for more than a century. Instruments carried on balloons, aircraft and satellites had measured them, revealing that they arrive from all directions, carrying energies far greater than anything produced in ordinary chemical reactions. Yet even with those measurements, much about cosmic rays remained uncertain. Where exactly did they come from? How did they travel across such vast distances? And what happened to them as they passed through the solar system? Voyager's journey toward interstellar space provided a rare opportunity to study these particles in a way that had never been possible before. As the spacecraft moved farther from the sun, the influence of the solar wind weakened, and the intensity of cosmic rays gradually increased. This allowed scientists to observe how the heliosphere shields the inner solar system, and what the cosmic ray environment is like beyond that protective bubble. To understand why cosmic rays are so important, it helps to consider their origins. Many cosmic rays are believed to be accelerated in the shock waves produced by supernova explosions, the violent deaths of massive stars. When such a star explodes, it sends a powerful wave of energy and matter racing outward through space. Charged particles caught in the expanding shock can be accelerated again and again, gaining energy each time they cross the shock front, until they are moving at speeds close to that of light. These particles, mostly protons but also heavier nuclei and electrons, then begin journeys that can last millions of years. Guided and scattered by magnetic fields in the galaxy, they wander through interstellar space, sometimes crossing entire spiral arms before eventually encountering regions like our solar system. There is something remarkable about that thought. A particle detected by Voyager today may have begun its journey in a star that exploded long before Earth existed. It may have travelled through clouds of gas, past newborn stars, across regions of the galaxy that no human has ever seen, before finally passing a spacecraft built by a small civilization orbiting an ordinary star. Cosmic rays carry information about these distant events. Their energies, compositions and directions provide clues about the environments in which they were accelerated and the paths they have travelled. By studying them, scientists can learn about processes occurring far beyond the reach of telescopes. Inside the heliosphere, however, cosmic rays are partially shielded. the solar wind and the sun's magnetic field act as a kind of barrier, deflecting many of the lower energy particles and reducing their intensity near the inner planets. This shielding is not perfect, but it is significant enough to affect the radiation environment of Earth and other worlds. As Voyager approached the heliopause, its instruments recorded a steady rise in cosmic ray intensity. Once the spacecraft crossed into interstellar space, the increase became even more pronounced. This provided direct evidence of how effective the heliosphere is at modulating cosmic rays and how different the environment is beyond it. One of the most striking observations was how sharply the intensity of certain cosmic rays increased at the boundary. It was as if the spacecraft had passed from a region of partial shelter into one where the full intensity of galactic radiation was present. This transition also revealed something unexpected. The boundary of the heliosphere appears to act not only as a shield, but also as a region where cosmic rays can be temporarily trapped or slowed. Measurements suggested that particles sometimes accumulate near the heliopause, influenced by the complex magnetic fields and turbulence in that region. These findings helped scientists refine their models of cosmic ray propagation, not only in our solar system but throughout the galaxy. Understanding how magnetic fields and plasma structures influence the motion of charged particles is essential for explaining observations of cosmic rays from distant regions. There is also a practical side to this research. Cosmic rays pose a hazard to spacecraft and astronauts, especially on missions beyond Earth's protective magnetic field. High-energy particles can damage electronics and increase the risk of radiation exposure. By studying the cosmic ray environment in detail, scientists can better understand the challenges that future explorers may face. Voyager's measurements have been particularly valuable because they provide a long-term record. The spacecraft has been detecting cosmic rays for decades, allowing researchers to observe how their intensity changes over time, influenced by the solar cycle and by the spacecraft's changing position. Another intriguing aspect of cosmic rays is their composition. Some are simple protons, but others are heavier nuclei, including elements such as carbon, oxygen, and iron. These heavier particles are fragments of atoms forged in the interiors of stars and scattered into space by stellar winds and explosions. In this sense, cosmic rays are not just messages from distant stars, but fragments of them, tiny pieces of matter that have travelled across the galaxy. The atoms in these particles were once part of stars that lived and died long before our solar system formed. There is something quietly humbling about that realization. The matter that makes up our world and even our own bodies was forged in similar processes in ancient stars that exploded and scattered their elements into space. Cosmic rays are reminders of that shared history, fragments of the same cosmic cycle that created the Sun, the Earth, and everything on it. Voyager's instruments can also measure the energy distribution of cosmic rays, revealing how many particles exist at different energy levels. This information helps scientists understand the mechanisms that accelerate these particles and the environments through which they travel. One of the surprises from Voyager's data was how smooth and steady the cosmic ray intensity became once the spacecraft entered interstellar space. Inside the heliosphere, the intensity varies more strongly with the solar cycle, rising and falling as the solar wind changes. Beyond the heliopause, these variations are smaller, suggesting that the interstellar medium provides a more stable environment for cosmic rays. This stability provides a kind of baseline, a reference point for understanding how much the heliosphere modifies the cosmic ray environment. It also offers insight into the conditions that exist throughout much of the galaxy, far from the influence of any particular star. Cosmic rays also play a role in the chemistry of interstellar space. When they pass through clouds of gas, they can ionize atoms and molecules, triggering reactions that lead to the formation of more complex compounds. In this way, they contribute to the processes that eventually lead to the formation of new stars and planetary systems. So these particles are not just passive travelers, they are active participants in the ongoing evolution of the galaxy, influencing the environments through which they pass. For Voyager, detecting cosmic rays is a relatively quiet process. There are no dramatic flashes or sounds, only the steady counting of particles as they pass through detectors, each one recorded, analysed and added to a growing record of the interstellar environment. And yet, behind those numbers lies a story that spans immense distances and timescales. A story of stars forming, shining and exploding, of particles accelerated to incredible speeds, of journeys lasting millions of years. As the spacecraft continues outward, the cosmic ray environment remains one of the most important aspects of what it is studying. Each measurement helps refine our understanding of how the heliosphere interacts with the galaxy and how radiation moves through interstellar space, but cosmic rays are only part of the picture. Beyond the heliopause, Voyager is also measuring other properties of the interstellar medium, including its temperature, pressure and density, parameters that reveal what conditions are really like in the space between stars, and that help answer a question many people have wondered about. What does it actually feel like in physical terms to be in interstellar space? Standing in interstellar space is something no human being has ever experienced directly, and it is difficult to imagine using everyday intuition. Most of what we know about that environment comes from instruments, equations, and patient interpretation of faint signals sent across enormous distances. Yet those measurements allow us to reconstruct, with surprising clarity, what the conditions are like in the vast regions between stars, the temperature, the pressure, and the darkness that define this remote part of the universe. One of the first things that often surprises people is the temperature. When we think of space far from any star, we tend to imagine it as unimaginably cold, and in one sense that is true. If you placed an object in deep space and allowed it to radiate heat freely, it would eventually cool to just a few degrees above absolute zero, only slightly warmer than the faint glow of the cosmic microwave background that fills the universe. However, temperature in interstellar space does not behave in the way it does on Earth. Temperature is a measure of the average kinetic energy of particles, how fast they are moving. In a gas that is extremely sparse, particles can move very quickly, giving the gas a high temperature, even though there are so few particles that the gas would not feel hot at all. There is almost nothing there to transfer heat. Voyager's measurements indicate that the local interstellar cloud, the region of space the spacecraft is currently travelling through, has a temperature of several thousand degrees Celsius. That number sounds dramatic, but it does not mean that a spacecraft would heat up to those temperatures. The density of particles is so low that collisions are rare, and very little energy is transferred to surfaces. A helpful comparison is the air inside a very high vacuum chamber on Earth. If you heat the walls of the chamber, the few remaining molecules inside may move rapidly, corresponding to a high temperature, but the chamber itself does not feel hot because there are too few molecules to carry heat effectively. Interstellar space is even more extreme in this regard. Pressure in interstellar space is also extraordinarily low, far lower than any vacuum we can create in a laboratory. Pressure depends on both the number of particles and their speed. In the interstellar medium, both are small by everyday standards, though the particles may move quickly. The result is a pressure so faint that it is difficult to grasp in familiar terms, and yet that faint pressure is enough to shape the heliosphere. Over billions of kilometers, even a very small force becomes significant. The balance between the outward pressure of the solar wind and the inward pressure of interstellar space defines the boundary Voyager has crossed. Another important property of the interstellar medium is its density. In the region Voyager is travelling through, there are roughly a few atoms per cubic centimetre, sometimes even less. To put that into perspective, a single breath of air contains more molecules than there are atoms in a volume of interstellar space the size of a large building. Despite this extreme thinness, the interstellar medium plays a crucial role in the life cycle of stars. Over millions of years, gravity can cause clouds of gas and dust to collapse, forming new stars and planetary systems. The material drifting past Voyager today may one day become part of a star, a planet, or even living organisms somewhere in the galaxy. Darkness is another defining feature of interstellar space. Far from stars, there is very little light. The Sun, seen from Voyager's distance, is just a bright star among many others, no longer the dominant source of illumination. The sky in interstellar space would appear much as it does from the outer solar system, filled with stars but without the bright glare of a nearby sun. Even the faint glow of sunlight scattered by interplanetary dust becomes weaker as one moves farther from the sun. The background of space grows darker, and the contrast between stars and the surrounding sky becomes sharper. There is, however, still some light. The Milky Way stretches across the sky as a broad band of distant stars. Individual stars shine steadily, and faint nebulae glow where clouds of gas are illuminated by nearby suns. Interstellar space is not completely black, but its light is gentle, distant, and sparse. Voyager itself does not carry instruments designed to capture images of this darkness anymore. Its cameras were turned off long ago to conserve power. But earlier missions and telescopic observations from Earth give us a good sense of what such a sky would look like. Another aspect of interstellar space that Voyager measures is the density and behaviour of plasma, the charged component of the interstellar medium. Plasma waves, which we discussed earlier, provide a way to measure how many charged particles are present and how they respond to disturbances such as shock waves from solar eruptions. These measurements have revealed that the density of plasma in interstellar space is higher than in the outer heliosphere, one of the key pieces of evidence confirming that Voyager has indeed crossed into a different environment. Magnetic fields are also present in interstellar space, though they are extremely weak compared to those we encounter on Earth. These fields influence the motion of charged particles, guiding cosmic rays and shaping the structure of interstellar clouds. Voyager's magnetometer has detected these fields, providing valuable information about their strength and orientation in our region of the galaxy. One of the most intriguing aspects of these measurements is how stable some of these conditions are over long periods. Unlike the solar wind, which varies with the sun's activity, the interstellar medium appears more uniform on the scales Voyager has sampled. This stability provides a baseline against which scientists can measure the effects of the heliosphere and the solar cycle. Time itself feels different when considering these environments. Changes occur slowly over years and decades, rather than minutes or hours. A disturbance from the sun may take more than a year to reach Voyager, and the effects of that disturbance may be detected long after the event that caused it has faded from memory on Earth. Communication with the spacecraft reflects these long timescales. Signals take more than 20 hours to travel one way, and the data received represents conditions that existed nearly a day earlier. Each exchange between Earth and Voyager is a reminder of the immense distances involved. There is also the matter of radiation. Beyond the heliosphere, the intensity of cosmic rays is higher, exposing Voyager to a harsher radiation environment than it experienced inside the sun's protective bubble. The spacecraft's instruments are designed to withstand this radiation, but over time it contributes to the gradual aging of electronic components. For future human explorers, this environment presents significant challenges. Spacecraft travelling beyond the heliosphere would need to provide protection against cosmic rays and other forms of radiation, something that is far less critical for missions confined to the inner solar system. The darkness between the stars is therefore not merely an absence of light. It is an environment with its own properties: temperature, pressure, density, magnetic fields, and radiation. These conditions shape the behaviour of matter and energy on scales far larger than anything we encounter on Earth. It is easy to overlook how extraordinary it is that we can measure these properties at all. Voyager's instruments, designed decades ago, continue to provide data about a region that no human has ever visited and that no telescope can study in quite the same way. Each measurement adds to a growing picture of the interstellar medium, revealing it not as an empty void, but as a subtle, dynamic environment, filled with particles and fields, shaped by the life cycles of stars and the structure of the galaxy. And as scientists continue to analyse this data, they are beginning to understand not only what interstellar space is like today, but also how it may have changed in the past and how it might change in the future as the Sun moves through different regions of the Milky Way. Because the solar system is not stationary. It is travelling through the galaxy, orbiting the galactic centre and passing through clouds of gas and dust over millions of years. The heliosphere and the environment around it respond to those changes, expanding or contracting depending on the density and pressure of the surrounding medium. This realization leads to another important question. If the conditions beyond the heliopause can vary, and if the heliosphere itself changes over time, what does that mean for the long-term history of our solar system? How different might the boundary have been millions of years ago, and how might it look millions of years from now? Voyager's journey provides only a snapshot, a brief glimpse of one moment in a much longer story. Yet even that snapshot has revealed more than anyone once expected, showing that the space between the stars is richer, more complex and more interesting than the empty darkness it was once imagined to be. Expectations in science often begin with models, and models, by necessity, simplify reality. Before any spacecraft had travelled to the outer boundary of the heliosphere, researchers relied on theory, laboratory plasma experiments, and indirect astronomical observations to predict what that region would be like. Those predictions were careful and well-reasoned, yet when Voyager finally reached the frontier, the details turned out to be more complicated than almost anyone had anticipated. Part of the reason lies in the nature of the heliosphere itself. It is not a solid structure, not even a stable fluid boundary, but a region shaped by many interacting forces. The solar wind flows outward from the Sun, carrying magnetic fields and charged particles. The interstellar medium presses inward, bringing its own particles, pressure and magnetic structure. Both of these influences vary over time. The Sun changes with its activity cycle, and the galaxy presents different conditions as the solar system moves through it. Trying to predict the precise behaviour of such a system is like trying to predict the exact shape of waves on a distant shoreline without ever seeing the ocean. The basic principles can be understood, but the details depend on countless small variations that are difficult to calculate in advance. One of the earliest expectations was that the heliopause would be relatively smooth and well-defined, almost like the surface of a bubble. Scientists imagined a transition where the solar wind would fade, interstellar particles would dominate, and the magnetic field would shift clearly from one orientation to another. That picture was neat, understandable, and appealing. Voyager revealed something more irregular. The boundary was not smooth. Measurements showed fluctuations in particle densities and magnetic fields, suggesting that the heliopause is a dynamic interface, filled with turbulence, waves, and localized structures. Instead of a single clean transition, the spacecraft experienced variations that sometimes made it difficult to determine exactly when the crossing had occurred. This complexity arises from the behavior of plasma, which is not a simple gas. Plasma responds strongly to magnetic fields, and magnetic fields can twist, reconnect, and form structures that evolve over time. At the boundary of the heliosphere, the solar magnetic field and the interstellar magnetic field interact in ways that produce patterns far more intricate than early models had captured. Another expectation that had to be revised involved the motion of the solar wind near the boundary. Earlier theories suggested that the solar wind would slow down steadily as it approached the heliopause, but Voyager detected regions where the outward flow nearly stopped altogether. In these areas, the balance of forces between the solar wind and the interstellar medium created zones of stagnation, where particles moved very little relative to the Sun. This was surprising because it implied that the boundary region contains pockets where conditions differ significantly from one location to another. Instead of a uniform layer, the heliosheath and heliopause appear to be structured and uneven, shaped by turbulence and variations in pressure. the behaviour of cosmic rays provided another unexpected result. Scientists had predicted that their intensity would increase as Voyager approached and crossed the heliopause, and this did happen. However, the details of that increase were more complex than anticipated. Rather than a smooth change, the measurements showed sudden jumps and plateaus, indicating that the boundary influences how cosmic rays propagate in ways that were not fully understood. These patterns suggested that the heliopause can act as both a barrier and a trap, temporarily confining particles or redirecting them along magnetic field lines. This realization has implications far beyond our own solar system, because similar processes are likely to occur around other stars. Even the shape of the heliosphere turned out to be different from what many had imagined. Earlier models often depicted it as a long, comet-like structure with an extended tail. More recent data, including observations of energetic neutral atoms and measurements from Voyager, indicate that the shape may be more rounded or divided into broad lobes rather than a single trailing stream. This change in understanding highlights how sensitive the heliosphere is to magnetic fields. The interstellar magnetic field, though extremely weak by everyday standards, exerts a significant influence over large distances. Its interaction with the solar magnetic field helps shape the outer boundary of the solar system in ways that are still being studied. Another reason the edge of the solar system was not what anyone expected is that conditions there depend not only on distance, but also on time. The solar wind carries information about the sun's activity outward through the heliosphere, but it takes years for that information to reach the outer boundary. This means that the conditions Voyager encountered were shaped by events that occurred on the sun many years earlier. Solar eruptions, changes in magnetic activity, and variations in the solar cycle all left their imprint on the plasma and fields in the outer heliosphere. As a result, the boundary region is influenced by a history of solar activity stretching back over a decade or more. Interstellar conditions also vary over time, though on longer scales. The local interstellar cloud through which the solar system is moving is not perfectly uniform. Its density, temperature, and magnetic properties change gradually from place to place. Over millions of years, the sun will pass into different regions, each with its own characteristics, and the heliosphere will respond accordingly. This dynamic environment means that the boundary Voyager crossed is not a permanent fixed structure. It is constantly evolving, expanding or contracting in response to changing conditions. If another spacecraft were to cross the heliopause in the same direction decades from now, it might encounter somewhat different conditions. There was also an element of surprise in the very fact that Voyager was able to reach and study this region at all. When the spacecraft were designed, no one could be certain they would continue operating for so many decades. Instruments were built to be robust, but the idea that they would still be sending data nearly half a century later was beyond even the most optimistic expectations. Because of this longevity, Voyager was able to provide a continuous record of the outer heliosphere over many years, revealing gradual changes that would have been impossible to observe in a shorter mission. That long perspective turned out to be essential for understanding the boundary region. The discoveries also changed how scientists think about the relationship between stars and the galaxy. The heliosphere is just one example of an astrosphere, a bubble created by a star's wind interacting with the interstellar medium. By studying our own astrosphere in detail, researchers gain insight into how similar structures behave around other stars, including those that host planets. This has implications for understanding cosmic radiation environments, planetary atmospheres, and even the potential habitability of distant worlds. A strong stellar wind and magnetic field can shield planets from high-energy particles, while a weaker one may leave them more exposed. Another unexpected realization concerned the role of turbulence in shaping the boundary. Early models often treated the heliopause as a relatively stable surface, but Voyager's data showed evidence of waves and instabilities that ripple through the plasma. These disturbances can alter the local conditions, affecting particle motion and magnetic field orientation. Turbulence is notoriously difficult to model, especially in magnetized plasmas, where small changes can propagate and interact in complex ways. The outer heliosphere turned out to be a natural laboratory for studying these processes, offering insights that are relevant not only to space physics, but also to astrophysics more broadly. There was also a philosophical aspect to the surprise. For many years, the solar system had been defined primarily by the orbits of planets. The idea that its true boundary lies far beyond the last planet, in a region defined by invisible forces and subtle interactions, required a shift in perspective. Voyager helped make that shift possible by providing direct evidence of the heliosphere and its boundary. It transformed an abstract concept into something real, something measured and observed, a frontier that could be crossed and studied. The edge of the solar system, it turned out, is not a sharp line but a region of transition, shaped by forces that operate across vast distances and timescales. It is a place where the influence of our star gradually gives way to the influence of the galaxy, where particles from distant supernovae mingle with those from the Sun, and where magnetic fields from different sources interact in subtle ways. Understanding this region required patience, collaboration, and the willingness to revise long-held assumptions. Each new piece of data from Voyager prompted new questions, new models, and new interpretations. The process is still ongoing, as scientists continue to analyze measurements and compare them with observations from other missions and telescopes. Perhaps the most important lesson from these discoveries is that the universe often resists simple descriptions. Boundaries are rarely sharp, structures are often more complex than they appear, and the interplay of forces can produce patterns that are difficult to predict. Voyager's journey to the edge of the solar system reminded us of that in a quiet but powerful way. It showed that even in regions we thought we understood in principle, there is always more to learn when we look closely enough. And as researchers continued to examine the data from beyond the heliopause, they began to focus on another question, one that naturally follows from everything Voyager has revealed so far. If the boundary of the solar system is complex, dynamic, and influenced by both solar and interstellar forces, what new discoveries might still be waiting in the data the spacecraft continues to send back? And what might those discoveries tell us about the future of Voyager itself and the long journey that still lies ahead? Even now, decades after the spacecraft left the planets behind, Voyager has not become merely a relic of past exploration. It is still returning information, still contributing to science, and still changing how researchers think about the outer reaches of our solar system and the space beyond it. The pace of discovery is quieter than during the dramatic flybys of Jupiter or Saturn, but the importance of what is being learned has not diminished. In some ways, the lessons arriving today are even more profound, because they concern regions that had never been observed directly before. One of the most important things Voyager continues to teach us is how the interstellar medium behaves over time. The environment beyond the heliopause is not static. Measurements of cosmic rays, plasma waves, and magnetic fields show gradual changes, indicating that the spacecraft is moving through regions with slightly different properties. These variations are subtle, but they matter. They help scientists understand how matter is distributed in our local region of the galaxy, and how conditions vary from place to place. This kind of information cannot be obtained from telescopes alone. Telescopes can observe distant clouds of gas and dust, but they cannot measure the properties of the interstellar medium at a specific location in the way a spacecraft can. Voyager provides what scientists sometimes call ground truth, direct measurements that anchor theories and observations. Another continuing lesson comes from the way cosmic rays behave outside the heliosphere. By comparing measurements taken over many years, researchers are learning how the intensity of these high-energy particles changes with time, and how they respond to disturbances propagating outward from the Sun. Even beyond the heliopause, events in the solar system can have detectable effects, because shock waves from solar eruptions travel vast distances and eventually pass the spacecraft, compressing the plasma and altering particle populations. These observations reveal that the boundary between solar and interstellar space is not a strict separation, but part of a connected system. The sun's influence, though weaker beyond the heliopause, does not end abruptly. It fades gradually, and disturbances can travel far beyond the region where the solar wind itself dominates. Voyager is also helping scientists refine their understanding of magnetic fields in interstellar space. Magnetic fields are difficult to measure at great distances, and their structure on small scales is not well known. The magnetometer aboard Voyager continues to record the strength and direction of the fields surrounding the spacecraft, providing valuable data about how these fields vary over time. These measurements contribute to a larger effort to map the magnetic structure of our part of the Milky Way. Magnetic fields play a crucial role in many astrophysical processes, from the formation of stars to the propagation of cosmic rays, yet they remain one of the more challenging aspects of the interstellar medium to study. There is also the lesson of longevity itself. Voyager was not designed with the expectation that it would operate for half a century, and yet, through careful engineering, redundancy, and patient management, the spacecraft continues to function. Engineers have learned a great deal about how materials and electronic components behave over extremely long periods in the harsh environment of space. These lessons are valuable for future missions, as plans are considered for probes that might travel even farther, perhaps designed specifically to explore interstellar space. The experience gained from Voyager provides a foundation. It shows what is possible, what kinds of failures may occur over decades, and how spacecraft systems can be managed to extend their lifetimes far beyond original expectations. The way the mission is operated today also reflects a kind of careful stewardship. Because the available power from the radioisotope generators decreases each year, mission controllers must decide which instruments to keep operating and which to turn off. Each decision involves balancing scientific value against the need to conserve energy. This process requires not only technical expertise but also a sense of patience and perspective. The goal is not to maximize data in the short term, but to extend the mission as long as possible, allowing Voyager to continue sending information for years to come. Communication with the spacecraft remains an extraordinary achievement in itself. The signals Voyager transmits are incredibly faint, weaker than the power of a small light bulb by the time they reach Earth. Detecting them requires the use of the Deep Space Network, a collection of large radio antennas located in different parts of the world, carefully coordinated to track and receive signals from distant spacecraft. Every time data is received from Voyager, it is a reminder of the distances involved. The spacecraft is so far away that radio signals take nearly a full day to travel one way. Commands sent today will not be received until tomorrow, and responses will not arrive until the day after that. The mission unfolds on timescales that encourage a different way of thinking, slower and more deliberate than most technological activities. Another area where Voyager continues to teach us is in the study of plasma waves. The oscillations detected in the interstellar medium provide ongoing measurements of particle density and reveal how disturbances propagate through this environment. Each new detection adds to a growing record, helping scientists understand how interstellar plasma responds to changes over time. These measurements also provide insight into the local interstellar cloud itself. By observing how density and other properties vary as the spacecraft moves, researchers can begin to map the structure of this cloud, learning whether it is uniform or contains regions of slightly different composition and temperature. There is something remarkable about the scale of these observations. Voyager moves about 17 kilometers per second, which is fast by human standards, but slow compared to the size of interstellar structures. It may take years for the spacecraft to travel through regions where conditions change only slightly. This means that understanding the data requires patience, careful analysis, and the willingness to look for patterns that emerge slowly over time. Voyager is also teaching us about the limits of our knowledge. Each discovery raises new questions. For example, scientists are still working to understand the precise shape of the heliosphere and how it changes over time. They are studying how cosmic rays interact with the boundary region and how magnetic fields from the Sun and the galaxy combine and evolve. These questions are not easy to answer, partly because we have only 2 spacecraft sampling the outer heliosphere in interstellar space, and both are travelling in specific directions. The picture we are building is detailed but still incomplete, like a map drawn from a few long narrow paths through a vast landscape. Future missions may one day expand that map, but for now, Voyager remains one of our most important sources of information about these distant regions. There's also a human lesson in all of this, a reminder of what persistence and curiosity can achieve. The Voyager mission spans generations. The people who designed and built the spacecraft worked in an era when computers were far less powerful than those in a modern phone. The scientists analysing the data today use tools and techniques that did not exist when the spacecraft was launched. And yet, across those decades, the mission has continued, sustained by a shared sense of purpose and wonder. Each generation of researchers inherits the work of the previous one, adding new insights and passing the mission forward. The data Voyager sends back may not always make headlines. There are no dramatic images now, no close encounters with planets. Instead, there are streams of numbers, measurements of particles and fields, subtle variations that reveal the properties of a distant environment. But within those numbers are answers to questions that once seemed impossible to address. There is also the lesson of scale. Voyager reminds us how vast the solar system truly is, and how small our everyday world appears in comparison. Even after travelling for nearly 50 years, the spacecraft has not come close to another star. It is still in a region that, on a galactic scale, lies very near the Sun. This perspective can be both humbling and inspiring. It shows us how far we have come in our ability to explore the universe, and how much remains to be discovered. As the years pass, the available power aboard Voyager will continue to decline. Instruments will be turned off one by one, and eventually, perhaps within the next decade, the spacecraft will no longer be able to transmit data. When that happens, the mission in its current form will come to an end. But even then, Voyager will still have something to teach us, because the spacecraft itself will continue its journey, carrying with it a record of who we were at the time it was launched. That record, the golden disc attached to its side, contains sounds, images and music from Earth, a message intended for any distant civilization that might one day encounter it. The existence of that record reminds us that Voyager is not only a scientific instrument, but also a kind of cultural artifact, a small fragment of human history travelling through interstellar space. And to understand why that message was included, and what it contains, it helps to look back at the moment when the spacecraft were being prepared for launch, when a group of scientists and artists began asking a simple but profound question. If you could send a message from Earth to the universe, what would you say? Few objects ever built by human hands carry a purpose as unusual as the golden records attached to the Voyager spacecraft. Bolted to the side of each probe, protected by an aluminum cover, and designed to endure the cold and radiation of interstellar space, these records were never meant to help navigate, measure particles, or transmit scientific data. Their purpose was something quieter and more symbolic. They were intended to carry a message, not to Earth, but outward, into the vastness of the galaxy. The idea began in the mid-1970s, as Voyager was being prepared for launch. Scientists and mission planners already knew that the spacecraft would eventually leave the planetary region and continue outward, possibly travelling through interstellar space for millions of years. That realization led to an unusual question. If these spacecraft might one day be encountered by another intelligent species, however unlikely that possibility might be, what should they carry with them? It was not a question with a simple answer. The chances of the record ever being found are extraordinarily small. Space is immense beyond ordinary comprehension, and the distances between stars are so great that even a spacecraft travelling as long as Voyager has will take tens of thousands of years to approach another stellar system. Yet the possibility, however remote, was enough to inspire the effort. A small team was assembled to design what became known as the Golden Record, The group included scientists, engineers, artists and writers, all working together to decide what should be included. Among them was the astronomer Carl Sagan, who helped guide the project and shape its overall vision. They faced a difficult challenge. The record had to represent Earth, not just one country or culture, but an entire planet. It needed to convey something about humanity, about life, about the diversity of experiences and environments that exist here. And it had to do so in a form that could, at least in principle, be understood by beings who might have no knowledge of human language or culture. The result was a phonograph record made of gold-plated copper, designed to be played at 16 2/3 revolutions per minute. Along with the record itself, the spacecraft carries a cartridge and a stylus, as well as engraved diagrams explaining how to play the record and how to interpret the information encoded on it. Those diagrams are themselves a kind of language, using fundamental physical concepts that scientists hoped would be universal. They include representations of the hydrogen atom, the most abundant element in the universe, and a map showing the position of the Sun relative to nearby pulsars, whose regular radio pulses can serve as cosmic landmarks. The contents of the record were chosen with great care. There are greetings spoken in dozens of languages, from widely used ones like English, Spanish, and Mandarin to others spoken by smaller communities. Each greeting is brief, a simple expression of goodwill, a way of saying, in effect, hello from the people of Earth. There are also natural sounds, recordings of waves on a shore, wind, thunder, birds, and other elements of the planet's environment. These sounds were included to convey something about the character of Earth itself, about the presence of oceans, weather, and living creatures. Music forms another large part of the record. The selections span a wide range of cultures and styles, from classical compositions by Bach and Beethoven to traditional music from various regions of the world, as well as blues and other forms that reflect more recent musical traditions. The goal was not to present a complete survey of human music, which would have been impossible, but to offer a glimpse of its diversity and emotional range. There are also images, encoded in analog form, that can be reconstructed by following the instructions engraved on the record's cover. These images include photographs and diagrams showing aspects of human life, scientific knowledge, and the natural world. There are pictures of landscapes, animals, plants, and people, as well as diagrams illustrating basic principles of mathematics and physics. One image shows the structure of DNA, the molecule that carries the genetic instructions for life. Another depicts the solar system, indicating the position of Earth and the path of the Voyager spacecraft. Others show everyday scenes, people eating, working, playing, and interacting, moments intended to convey something about how life is lived on this small planet. Choosing these images was not easy. The team had to decide what aspects of humanity and Earth were most important to represent. They debated which cultures, which activities, which scientific ideas should be included. Inevitably, the selection could never be complete, but the effort itself was meaningful, an attempt to create a portrait of a world in a limited space. There is something deeply thoughtful about the tone of the record. It does not boast or exaggerate. It does not present humanity as powerful or dominant. Instead, it offers a simple introduction, a collection of sounds and images, a quiet statement of existence. The record also includes a printed message from the Secretary General of the United Nations at the time, expressing hope for peace and friendship among civilizations wherever they might be found. That message reflects the spirit in which the record was created, not as a declaration of achievement, but as a gesture of connection. It is interesting to consider what it would be like to encounter such an object without any prior knowledge of its origin. A small, silent machine drifting through interstellar space, carrying a golden disc engraved with unfamiliar symbols, containing sounds and images from a distant world. The effort to interpret such a message would require patience, curiosity, and perhaps a sense of wonder similar to what humans feel when studying signals from distant stars. Of course, the most likely outcome is that the record will never be found. Voyager is travelling through a region of space so vast and sparsely populated that the probability of a close encounter with another civilization is extremely low. Over millions of years, the spacecraft may pass through interstellar clouds, approach distant stars, or continue drifting in the outer regions of the galaxy without ever being noticed. Yet the value of the Golden Record does not depend on its being discovered. Its creation was meaningful in itself. It required people to think about who they were, what they valued, and what they would want to say to the universe if given the chance. In that sense, the record explains as much about humanity to ourselves as it does to any potential listener. It reflects a species capable of curiosity, creativity, and reflection, willing to send a message across unimaginable distances even without any expectation of reply. There is also something quietly moving about the physical durability of the record. Designed to last for billions of years under the conditions of interstellar space, it may outlast the continents, the oceans, and perhaps even the sun itself. Long after the last signals from Voyager have faded, long after the spacecraft's instruments have fallen silent, the record will remain, orbiting the centre of the Milky Way along with countless other objects. It will carry with it the sound of wind and waves, the laughter of people, the music of instruments played by hands that have long since turned to dust. It will carry images of a blue planet, a small star, and a species that looked up at the night sky and wondered what lay beyond. There is a certain humility in that gesture. The record does not claim that humanity is unique or central to the universe. It simply offers a greeting, an introduction, a small piece of information sent outward in the hope that it might one day be received. For the scientists and engineers who worked on Voyager, the inclusion of the Golden Record was a reminder that exploration is not only about gathering data, it is also about meaning, about the human desire to understand and to be understood, to reach outward and make contact, even if only symbolically. As Voyager continues its journey, the record remains attached to its side, carried silently through interstellar space. The spacecraft itself will eventually cease transmitting, but the record will endure, a silent ambassador travelling through the galaxy. And the journey itself is far from over. Voyager is still moving, still leaving the sun farther behind with each passing year. The distances it will travel in the future are almost impossible to imagine, measured not in years or decades, but in tens of thousands of years. Considering how long the spacecraft will continue its journey, and what lies ahead over those immense stretches of time, leads naturally to another question. What will happen to Voyager in the far future, and how long will it continue travelling through the darkness between the stars? Time behaves differently when you begin to think in terms of interstellar travel. The scales involved are so large that even decades begin to feel like brief moments, and centuries pass in the span of a single calculation. Voyager, already travelling for nearly half a century, is still only at the very beginning of its journey through the galaxy. At this moment, both Voyager spacecraft are still operating, though with limited power. The electricity that keeps their instruments running comes from radioisotope thermoelectric generators, devices that convert heat from the slow decay of plutonium into electrical energy. This power source does not stop suddenly. Instead, it declines gradually, year after year, as the radioactive material decays and the efficiency of the generators decreases. Because of this steady decline, engineers have had to manage the spacecraft carefully, turning off instruments one by one to conserve energy. Systems that were essential during planetary flybys are no longer needed, and shutting them down allows the remaining instruments to continue operating longer. Even with these careful measures, the available power will eventually fall below the level needed to operate the transmitters that send data back to Earth. Current estimates suggest that this may happen sometime in the 2030s. When that day arrives, Voyager will no longer be able to communicate. The stream of measurements that has continued for decades will come to an end, not because the spacecraft has stopped moving, but because it will no longer have the energy to speak. That moment will mark the end of the mission in its current form, but not the end of Voyager's journey. The spacecraft will continue travelling through interstellar space indefinitely, carried forward by its momentum. There is no air resistance in space to slow it down, no friction to bring it to a halt. Its path will be influenced only by the gravitational pull of stars and the large-scale structure of the galaxy, forces that act slowly and gently over immense distances. To appreciate how long this journey will continue, it helps to consider Voyager's speed and the distances between stars. Voyager 1 is moving at about 17 kilometers per second relative to the Sun. That is fast enough to cross the entire Earth in less than an hour, yet on a galactic scale it is modest. At that speed, it will take Voyager more than 40,000 years to come within about 1.6 light-years of another star, Gliese 445, a faint red dwarf in the constellation Camelopardalis. Even then, it will not enter orbit or come particularly close by astronomical standards. It will simply pass through the outer regions of that star's distant gravitational influence and continue on its way. Voyager 2, travelling on a slightly different trajectory, will have its own distant encounters over tens of thousands of years, passing relatively near other stars as it orbits the centre of the Milky Way, along with the Sun and billions of other objects. These timescales are difficult to grasp. 40,000 years is longer than the span of recorded human civilization. When Voyager makes its closest approach to Gliese 445, the continents on Earth may look different. Languages will certainly have changed, and humanity itself may have evolved culturally or technologically in ways that are impossible to predict. And still, Voyager will be travelling, silent but intact, a small artifact of a distant past. Over even longer periods, the spacecraft will continue orbiting the centre of the galaxy. The Sun itself takes about 225 million years to complete one orbit around the Milky Way. Voyager will share that journey, moving along a similar path, though not exactly the same, influenced by gravitational interactions over time. Eventually, over hundreds of millions or billions of years, the spacecraft may pass near stars, be perturbed slightly by their gravity, or drift through interstellar clouds. The exact details are impossible to predict so far into the future, but one thing is certain: the spacecraft will remain in motion for a very long time. The physical structure of Voyager is also likely to endure for immense spans of time. Interstellar space is a relatively gentle environment in some ways. There is no atmosphere to cause corrosion, no weather, no biological activity. Micrometeoroids and cosmic radiation will gradually erode and damage the spacecraft, but these processes occur slowly. The golden record attached to Voyager was designed to survive for hundreds of millions, perhaps billions of years under such conditions. Its gold plating protects it from corrosion, and its cover shields it from dust and radiation to some extent. If the spacecraft is not destroyed by a collision or intense radiation near a star, the record may persist long after the Earth itself has changed beyond recognition. There is something remarkable about the idea that a small object built by human hands could outlast mountains, oceans, and perhaps even species. It reminds us how different the timescales of astronomy are from those of everyday life. Voyager's journey also raises interesting questions about the future of exploration. The spacecraft was not designed to reach another star. Its speed, though impressive, is far too low for interstellar travel on human timescales. Future missions may use entirely different technologies, perhaps advanced propulsion systems or entirely new methods of travel, to cross the distances between stars more quickly. Yet Voyager will always hold a special place in history as the first object to leave the heliosphere and enter interstellar space. It is the pioneer, the pathfinder, the first step into a much larger universe. Even after communication ends, scientists will continue to study the data Voyager has already returned. Decades of measurements from the outer heliosphere and interstellar medium will remain valuable for years to come, providing insights into plasma physics, cosmic rays, and the structure of our local region of the galaxy. There is also a symbolic aspect to Voyager's continuing journey. It represents a kind of long-term thinking that is rare in human endeavours. The people who designed and launched the spacecraft knew that much of its journey would take place long after their own lifetimes. They built it anyway, not for immediate reward, but for the sake of discovery and understanding. That perspective can be inspiring. It reminds us that some of the most meaningful projects are those that extend beyond the present, that contribute to knowledge and exploration in ways that future generations will appreciate. It is also worth considering that Voyager is not entirely alone. The two spacecraft, Voyager 1 and Voyager 2, are travelling in different directions, each carrying its own golden record, each following a path that will take it through different regions of the galaxy. Together, they form a kind of quiet pair of ambassadors, drifting outward into the unknown. The signals they send back today are faint, but they are still being received, still being decoded, still adding to our understanding of the universe. Each transmission is a reminder that the journey continues, that the spacecraft are still out there, moving steadily farther from the sun. Eventually there will come a time when the last instrument is turned off, when the final signal fades into silence. That moment will not be sudden or dramatic. It will come quietly, the natural end of a mission that has lasted far longer than anyone originally expected. But even then, Voyager will not stop. It will continue travelling, silent and unseen, carrying with it a small piece of Earth and a record of who we were at the time we first reached beyond our planetary neighbourhood. There is a particular feeling that comes when you reach the edge of something familiar. It might happen at the shoreline of a vast ocean, where land gives way to water, or at the edge of a forest where the trees' thin and open ground stretches beyond. The mind becomes quiet in those moments, aware of both what is known and what lies beyond reach. Standing at the edge of the solar system, in a way, brings a similar feeling, though on a scale so large that it can only be understood through imagination and careful thought. Voyager has carried us, not physically but intellectually, to such a shore. Through its instruments and the steady flow of data over decades, it has allowed humanity to approach a boundary that once existed only in theory. It has shown us that the region around our sun is not infinite, that it has structure, layers, and a frontier where the influence of our star gradually fades into the broader environment of the galaxy. For most of human history, the idea of a boundary to the solar system would have seemed strange. The night sky appeared as a dome of stars, distant and unreachable, and the space between them was imagined as empty. Even after telescopes revealed the planets as worlds and meaningfully extended our sense of distance, the true scale of the solar system remained difficult to grasp. The planets felt like the outer limit, a natural boundary beyond which there was simply more darkness. Yet Voyager revealed that the darkness itself has structure. The solar wind, the heliosphere, the heliopause, the interstellar medium, each of these layers adds depth to our understanding of where we are. The solar system is not just a collection of planets orbiting a star. It is a region shaped by flows of particles, magnetic fields, and subtle pressures that extend far beyond the orbit of the most distant world. Thinking about this can change the way one looks at the night sky. Every star visible overhead is surrounded by its own region of influence, its own astrosphere, shaped by stellar winds and interactions with the interstellar medium. The galaxy is filled with these overlapping bubbles, each one marking the presence of a star and the space it shapes around itself. Our own heliosphere is just one among billions, a small temporary structure in a vast and dynamic universe. There is something both humbling and comforting in that realization. Humbling, because it reminds us how small our familiar world is in comparison with the galaxy. Comforting, because it places us within a larger context, part of a universe that operates according to consistent laws, where the processes shaping distant stars are related to those shaping our own sun. Voyager's journey also invites reflection on time. The spacecraft has been travelling for decades, longer than many people have been alive, and yet it has only begun its passage through interstellar space. The distances between stars are so immense that even the fastest spacecraft we have built move through them slowly, requiring tens of thousands of years to approach another star. This perspective stretches the imagination. It encourages a way of thinking that extends beyond individual lifetimes, beyond generations, into spans of time that feel almost geological in their scale. Voyager was built by people who knew they would never see the end of its journey, yet they built it anyway, trusting that future generations would continue to listen, to learn, and to wonder. There is a quiet beauty in that kind of long-term thinking. It reflects a belief that knowledge itself is valuable, that exploration is worthwhile even when the results unfold slowly, over decades or centuries. In a world that often moves quickly, where attention shifts from one moment to the next, Voyager represents patience, persistence, and continuity. It is also a reminder that exploration does not always require grand gestures or dramatic leaps. Sometimes it is the steady accumulation of small measurements, the careful analysis of faint signals, the gradual refinement of understanding that leads to the most meaningful discoveries. Voyager did not rush to the edge of the solar system. It arrived slowly, year by year, its journey measured in quiet increments of distance and time. Standing at the shore of the unknown, whether literal or metaphorical, often brings a sense of curiosity mixed with calm. The unknown is not always something to fear. It can also be something to approach gently, with patience and openness, allowing understanding to unfold gradually. This is perhaps one of the lessons Voyager offers. The universe is vast and much of it remains unexplored, but the process of exploration itself can be calm, deliberate and thoughtful. It does not always require urgency. Sometimes it requires only the willingness to continue, to keep asking questions and to keep listening. There is also a deeply human element to this story. Voyager carries the Golden Record, a small collection of sounds and images representing life on Earth. That record is unlikely ever to be found, yet its presence gives the mission a symbolic dimension. It is a gesture of communication, a way of saying that we were here, that we were curious, that we looked outward and wondered what lay beyond. Reflecting on that gesture invites another thought. Exploration is not only about discovering the universe, it is also about discovering ourselves, about understanding what we value, what we hope, and what we choose to carry with us when we venture into the unknown. The story of Voyager is not just a story of science and engineering. It is also a story of imagination, of people who dared to think on a scale far beyond their own lives, who built machines to travel farther than any human could go, and who listened patiently for whispers of information carried across billions of kilometers. And in those whispers, they found not only answers but new questions. What lies beyond the local interstellar cloud? How does the heliosphere change as the sun moves through the galaxy? What will future spacecraft discover as technology advances and exploration continues? These questions remain open, waiting for the next generation of explorers and instruments. Voyager has taken the first step, but it is only the beginning of a much longer journey for humanity, a journey that may one day carry probes, and perhaps even people to other stars. For now, Voyager continues to travel, silent and steady, moving farther from the sun with each passing year. Its instruments still measure particles and fields, still send back data, still add to our understanding of the universe. And even when those instruments fall silent, the spacecraft itself will continue onward, a small, enduring presence in the vastness of interstellar space. There is a certain peace in imagining that slow, quiet motion, a spacecraft drifting through the darkness, surrounded by distant stars, carrying with it a record of a small blue planet and the beings who once looked up at the night sky and wondered what lay beyond. Perhaps, in a way, that image mirrors something within us. The sense of curiosity that led to Voyager's creation is the same sense of curiosity that has driven exploration throughout human history, from the first journeys across oceans to the first steps on the moon. It is a gentle, persistent impulse to move outward, to learn, to understand. And so, as we think about the edge of the solar system and the space beyond, it can be calming to remember that we are part of this vast universe, not separate from it. The atoms in our bodies were forged in ancient stars. The light we see at night has travelled across immense distances to reach us. The spacecraft we build carry pieces of our knowledge and our hopes into the darkness, extending our presence in ways that would once have seemed impossible. If you let your thoughts rest there for a moment, imagining the quiet of interstellar space, the steady motion of Voyager, and the immense, slow rhythms of the galaxy, there is a kind of stillness that emerges. The universe is vast, but it is also patient. Its processes unfold over millions and billions of years, far beyond the pace of everyday concerns. And somewhere out there, beyond the planets, beyond the fading glow of the sun, Voyager continues its journey, a silent traveller moving through the darkness, reminding us that the shore of the unknown is not a place we reach once, but a horizon that moves with us, always inviting us to look a little farther, to wonder a little more, and to rest for a while in the quiet sense of awe that comes from knowing how vast and remarkable the universe truly is.